So thank you everyone for participating in this parallel session about electromagnetic counterparts of compact binary mergers. The first talk of the session will be a review about mainly observations of the recent GW 170817 by Raffaella Margutti.
All right. Thank you so much for having me today. So I'll start off with sort of a quick overview of the observations that we took for 170817, and then I will spend some time focusing on what is happening right now, which I believe is maybe the most exciting thing right now. So I don't have to tell this audience that 170817 is still the only event for which we were able to find gravitational waves and light, and that we were able to detect this event effectively across the entire electromagnetic spectrum. Mainly thanks to the extreme proximity of this neutron star merger at 40 megaparsec in this beautiful host galaxy, we were able to understand a lot of things that were completely out of reach for the general population of short GRBs. And here is a plot that I put together for the review paper, where I put there all data in the radio, optical, and X-rays that have been collected by actually a lot of you sitting in the audience and modeled by many of you that are also listening to this talk. So if we have a look at the spectrum of this event all the way to 900 days, is maybe one of the most boring spectra, of the most boring ACDs, with this beautiful, but still beautiful, simple power law that extended all the way from the radio to the X-rays for over 3 years. So this is beautiful when we try to infer some fundamental properties of the physics of particle acceleration in shocks. However, as we know very well, the fact that the spectrum did not contain information about break frequencies of the spectrum, of the synchrotron spectrum, so the fact that we just know that nu-c, the cooling frequency, is above the X-rays, and nu-m is below the radio. This is part of the reason why for this event, in spite of being extremely close by, we have to leave with a lot of degeneracies in the parameters. And in my mind, one of the most important of these degeneracies is the one that is related to the structure of this jet. We have a beautiful beautiful talk scheduled for later today. But here, the point that I'm trying to bring home is that while we do know that the shape of this light curve, the rise of this light curve, does contain information about how the energy and the Lorenz factor was distributed as a function of the angle. While we do know that that is a clear signature of that, what happens is that multiple jet structures effectively can fit the light curves and the data that we have. So if we have a look at the light curve as a cartoon, and we try to understand why we have this model of degeneracy, the picture can be simplified in this way. And I would like to point everybody that is not familiar with this literature with the literature that I list in the corner in the bottom right. So we do have effectively, even if we just focus on the jet core, we have around 8 parameters that are unknowns. And if we have a look at the properties that we can constrain with our observations, and we list them all, what happens is that even if we completely neglect that eta n parameter, which is the fraction of electrons that participate into the power load that produces this synchrotron, even if we assume, as we all do in the gamma burst literature, that 100% of electrons participate there, what we have is effectively a number of constraints that are way less, with fewer constraints than the unknowns that we have. So we have a beautiful way to constrain the power load slope of the spectrum, which gives us a measurement of the electron index distribution. We do have another constraint from the rise time, another constraint that is coming from when the light curve peaks. And we do have another constraint coming from the peak of the afterglow. And then we start counting. We have 4 constraints. We have, let's say, 7 open free parameters, which means that this problem is fundamentally under-constrained. Thanks to the VLBI observations by Kunal, I'm sure we're going to be hearing about that later today by Kunal and Giancarlo Ghirlanda. We had another constraint to the model, but still we are still dealing with 5 constraints and 7 free parameters. That means that there is no way we can really pin down the microphysics, for example, of this shock. And this is the reason, fundamentally, the fundamental reason why for this jet afterglow, we have a set of parameters or combination of parameters that are very well constrained, like the ratio of the kinetic energy to the density of the environment where this jet shock is expanding. However, when we start thinking about the 2 individual parameters, the density and the kinetic energy, individually, those 2 parameters are not as well constrained. So, however, the VLBI constraint allowed us to understand and constrain effectively the jet core opening angle and the off-axis angle, which is one of the things that we really needed to go from the observed rates into intrinsic rates. There is one open question in the field that, in my opinion, is extremely, maybe one of the most interesting, which is how many of these neutron star mergers do produce jets? And we do know that 17 did produce one ultra-relativistic successful jet, and now one of the most interesting questions is how many of these neutron star mergers do that. And if we compare their rates of neutron star mergers from LIGO and the inferred rate that we can calculate now from 17, the answer is that as of now, statistically speaking, the situation is still consistent with all neutron star mergers producing successful jets. And here I'd like to point you to some beautiful literature by our session organizer, Paz Benemini, if you're interested to know more about this. So where do we go from here? So here is, I would like to spend a lot of time today with you trying to understand where we are and what is happening right now. So the 2 things that we can do now that we know of 1708-17, of the jet of 1708-17 is, well, let's see what is the future of 1708-17. So right now it's still detectable. The signal is still detectable in the X-rays at least. And that means that as of almost 4 years almost after the merger, we're really exploring a phase space that we have never seen for neutron star mergers. And today I'd like to explore 2 potential explanations for what we will see is a potential deviation from the jet afterglow, which is maybe the emergence of a new component like a Kilonova afterglow component, or maybe some accretion-powered X-ray emission from the black hole that was formed by the neutron star merger. The other direction for to advance the field is, of course, going from the study of 1708-17 into a study of a population of binary neutron star mergers. So here I put there a snapshot of all the authors of the paper by my grad student Aprajita Ajela. That is my way to say a big thank you to each of them for their contributions. So this paper by Aprajita would not have happened without the contribution of each single individual here. So here is the punchline. You can look at the picture right there. You can see that as of 3.5 years after the merger, there is still a beautiful X-ray source. So you can see with your eyes. Those are a few photons, but extremely precious photons. And you can see that in the radio, we have maybe a tentative detection, but nobody has yet has called the radio detection. And we will see the details in a second. So here is a plot of the X-ray evolution with time, and you can see the data points. And what you can clearly see is that at the very late times, And with this, I mean, after 900 days, you can see that with a large error bars, yet you can see that there is a deviation compared to what you'd expect from the evolution of a jet afterglow. And here we are in the post-jet break part of the evolution of the jet, where the emission should behave like a beautiful T to the minus P power law. So, and those are the two observations from our campaign that led to the study that I'm going to present in a few seconds right now. So there is confusion right now in the literature about the significance of this axis. So I would like to spend just one slide with you to review the reason why there is actually no tension at all and why there might be some confusion right now. So first of all, maybe you might be thinking that there is a problem with the flux calibration of the X-rays, which is absolutely not true. The X-ray fluxes that you would infer if you assume the same parameters are statistically speaking equivalent. Statistically speaking, they are equivalent. So when it comes to evaluate the presence or absence of an axis compared to a model, here are the key steps that needs to be taken in this particular part of the parameter space. So here we are in a time where over 200 kiloseconds is as much time that we invested in the last data point you see there. In 200 kiloseconds, we had 16 photons. So we are in a regime where the Poisson nature of the signal, the Poisson nature of the process needs to be taken into account and this needs to be done in a very self-consistent way, both for the source and for your background. It needs to be done both at the time of the flux calibration, but also at the time of fitting. We can't fit a model and use the chi-square statistics to understand if that model is correct or not. That means that if you want to fit a model and you put all of your data points together, well, you need to be very careful and not treat with the same statistics the last two data points. If you do that, that's wrong. So second is absolutely important, since we're dealing with few data points, a few photons effectively, to avoid using average instrumental responses and instead account for the specific condition of the instrument at the time when the instrument was acquiring observations. If the observations were acquired over multiple days, well, the instrument was not in the very same conditions, and it is absolutely mandatory to account for that. Otherwise, there are little changes that in the final results. And then, very important, the statistical tests that we carried out needs to be carried out in the count phase space. And that's the only way to properly account for the Poisson nature of the signal, not in the flux phase space. Second, what we want to test for is a deviation compared to a model that described the data at earlier times. So the question, the statistical question that we're trying to answer is, until 900 days, this was the model that best fit the data. Do I see evidence for a deviation compared to that model? It's a different statistical question if we refit the data entirely, and then we ask, is there a deviation compared to a model that we refit? And then another point, of course, whatever model we decide to compare to, that model needs to be able to account for all the other existing observational constraints. So it's not okay to fit a new model that accommodates the latest data points, but at the expense of creating tension with other results, like the VLBI results. That's absolutely not the way to go. And finally, as much as it is possible, we would like to compare this potential axis to a model that is the least possible sensitive to assumptions about the jet structure. So all of these are the key steps that needs to be taken to assess the statistical significance of a potential axis here. And I also want to be very clear and emphasize that we do not claim any rebrightening here. There is no evidence at all for a rebrightening of the X-ray. So what we are saying is that there is the statistical evidence that we will see that I'll quantify in the next slide for an excess compared to the previous model, which is very different than saying that there is a rebrightening. So just to make you appreciate that we are really, really counting photons here in 100 kiloseconds and 100 days, we had 8 photons, and 200, we had 16 photons. And the other important aspect of this very low number statistics is that the energy of each single photon that hit the detector needs to be properly accounted for, as well as its uncertainty. If these steps are not done properly, then we can have discrepancies in the claimed results. So if you do all I showed in the previous slide, the conclusion is that right now, the cumulative statistical significance of this axis, where cumulative means taking all the data after 900 days, is at the level of 3.5 to 4.3 sigma. And here I'm talking Gaussian equivalent just because I find the 99.9945678, you tell whatever number you want, completely counterintuitive. The statistics is not Gaussian. I'm talking in Gaussian equivalent. The range that I'm giving, it depends on when we start fitting, in this case, the data with an asymptotic power law. And you go from 3.5 to 4.3 sigma. At the end, my personal thinking, my personal view is that at the end, time will tell if this excess is there or not. We do have another observation planned, which is, as the previous ones, is a Chandra and VLA, a very deep set of observations. And as before, our observations are public. And this will be taken in December, this December. So let's stay tuned and see if this excess is there or not. So let's have a look now. So now that we concluded that there is this excess with this limited significance, but it's there. Now let's have a look at the SED, broadband SED, and let's ask the question about, do we see any deviation compared to that power law that was always the same for 900 days? And again, accounting for Poisson statistics, the answer to this question is that there is limited evidence, but there is some suggestion of a hardening of the spectrum. And you can see that the confidence level there is at the level of 90%, 92% confidence level. So what we're dealing with is something that showed some little excess of X-rays at the level of 3.5 or 4 sigma, and some suggestion of a hardening of the spectrum. And those two observations are extremely exciting, in my opinion, as they might signal the emergence of a new emission component. So what I want to do in the last 7 minutes is to see, okay, now that maybe I convinced you that something is there, so what that can be. Well, and the two options that we considered in the work are a Kilonova afterglow. That was something that was pointed out by other authors before, theoretically, and or black hole accretion, so accretion powered X-ray luminosity. That is actually an idea by Brian, and Brian will talk just after me. I don't have time to go into details, but the afterglow evolution of the jet is unlikely to be able to account self-consistently for these two the two observations. So I'm sort of running out of time, so I'll go a little bit quick here. So until now, we have seen synchrotron from the jet shock. And what might be happening right now is that the Kilonova ejecta, much heavier than the shock from the jet, is now decelerated, and synchrotron emission from this Kilonova ejecta is now emerging, and that's why we call it Kilonova afterglow. So the reason why this is so beautiful, if this is what we're looking at, is the following. The optical, if you call the thermal part of the emission of the Kilonova that Brian will be talking about later, I believe, is the one that carries the bulk of the energy of the Kilonova ejecta, just like in supernova explosions. However, this part, it does not tell us much, and actually probably almost nothing about what is the fastest ejecta in the distribution of the Kilonova ejecta, and also how was the energy partitioned in the Kilonova ejecta. And here I used the parameterization by Adithan Kathir Kamaraju, where we parameterize the energy in the Kilonova ejecta as a power law in specific momentum with index alpha. The reason why it would be so great if we could understand what this alpha is because this alpha is related to the nature of the remnant, which is another big open question in our field. So what was left behind? So if you look at this plot, you can see that the different alphas that I put here, the different alphas of this kinetic energy profile, of these alphas map into a different evolution of the X-ray and broadband synchrotron emission from the Kilonova Afterglow, which are all of those dashed lines that you can see there. Which means that while right now the phase space is completely degenerate, as you might guess, we have very little information. In principle, if this component is really a Kilonova afterglow, and if we stay there and keep monitoring this Kilonova afterglow, eventually we should be able to understand the parameters of this of what is producing the synchrotron emission and also the stratification index maybe. So the other reason why it would be so great if we could say, yes, this is the stratification index of this Kilonova ejecta, is because the presence or absence of this fast tail of Kilonova ejecta is very deeply related to other pieces of the story, and specifically to the potential explanation of the gamma rays as a breakout, as a cocoon shock breakout, as well as the potential presence of a UV bright, very short-lived but UV bright emission component that was not seen for 170817, but might be there, which is a free neutron component that Brian might be telling us about. If you look at the same afterglow in the radio, this is how it would look, and you can see that the radio is actually in my mind, I thought that the radio would have been the place to look for any deviation, but instead the X-rays were the first one to point to the potential deviation. So very quickly, I want to touch base on the other potential explanation that is as exciting, if not even more exciting than a Kilonova afterglow, which is potential accretion that is coming from the remnant. And here, the story is that this synchrotron, this is might not even be synchrotron emission, and it's not coming from the outside, it's coming from deep inside. So the first thing to check is, can these X-rays escape if they are produced deep down there? And as you can see, it is reasonable to expect for the parameters of the ejecta mass and opacity and velocity, it is reasonable to expect that the X-rays might be able to escape on the relevant time scale. So that's okay, that's done. They could escape. So now if we try to have a look at more quantitatively, if there's a potential accretion on this remnant could explain the X-rays, we can use this plot here. So what you have, first of all, the level of the X-ray luminosity is around 5, 10 to 38, that I believe 20 theorists really smells like Eddington luminosity. So you can see the expected fallback luminosity with the very typical T to the minus 5/3 decay, and what we expect in red if we account for the absorption by the ejecta around. The other very beautiful part of this model is that it does naturally offer an explanation of why the excess will be in the X-rays. So here you can see one of the equations contributed by Brian, actually, where you can see that the temperature that we expect from this emission is of the order of a few keV, which is great, is right where we're observing right now. So this model naturally produces this effective temperature. As you can see in this plot, we also put with the dotted blue line the level of luminosity for a spinning down magnetar. You can see that the B field that we would require to explain the current level of luminosity is actually very low, and that's why we do not favor this scenario. So I believe Brian might tell us more about this aspect of the potential fact that we are seeing X-ray from accretion on a black hole remnant by this neutron star merger. So just to wrap up, so where do we go from here? We have to wait, and let's just stay tuned. December 2021 is when we will go back on target with both Chandra and DPVLA, and that will tell us what is going on. It will definitely tell us if that excess is still there or if it was a stochastic fluctuation of the signal. And that is all. And I'm very happy to take questions if you have any.
Thank you very much. Are there any questions? You can raise your hand virtually, yes?
Hi, Rafael, great talk. I was wondering what the actual physical extent of the emission site for the Kilonova afterglow is.
The extent? What do you mean?
Like how far from the merger site is the emission being produced? Yeah,
so the Kilonova shock. So if we believe that what is producing the emission is the fastest tail of the Kilonova ejecta, that is 0.8 C, 0.6 to 0.8 C, and so multiply that by T, and you get where physically that is produced.
So that would be that fast tail. Is that the stuff in the collisional plane that comes out the poles, or is there ejected that fast in the equatorial plane?
Yeah, so the model is agnostic. To tell the truth, the model is agnostic. What we do is just understand how much mass and what is the velocity that we would need to produce that synchrotron emission. And then the theorists can tell us, yes, we have that mass produced that way, but the emission on its own would not be able to tell you if it is equatorial, if it is on the pole. That is something we can't constrain from observations.
Thanks.
I was just say theoretically you can get both pole and equatorial material moving fast. Anyways.
Yeah, this is mildly relativistic, so the difference in viewing angle doesn't change much, depending on where the emission is coming from.
Are there any more questions? If not, then I have a few.
Well, I can ask a quick question.
Now you raise your hand, yes.
All right, thanks for the talk, Raf. I think this new observation is going to be extremely important, so thanks for proposing. But really, are we at a stage where we can distinguish between statistical fluctuation and just perhaps a flattening? Because it's so much at the edge of detection, right? So, I mean, what do we need, like, in order to say, yes, it is this explanation, or no, it is that explanation?
So if your question is there a statistical deviation from a t to the minus p power law decay, then the next observation with 100 kiloseconds, if the rate of photons that we detect is at least as large as the one that we did detect right now, then the significance is going to be way above the 4 sigma. So the answer will be yes, that is not the model that...
right, but it's going to be still hard to distinguish between models at that stage, I think, which is quite a challenge because it's really at the threshold of detection. Then you cannot distinguish between, like, let's say some wide angle outflow is taking over, or whether it's fallback accretion, or whether it's Kilonova afterglow. It's so much at the edge of detection, right? So, I mean, distinguish between models is going to be hard, I think.
That's where radio will be very important, right?
Sorry?
That's where radio will be very important.
Yeah, exactly. Yeah. So right now, what we would need is the signal to increase a little bit in the radio and to give us a solid detection. And then things, or maybe never do that. And the X-ray, if the X-rays go up and the radio stays where it is right now, that is also a clear signature that you're not looking at the same jet shock as before. Detection-wise, the detection is very solid in the X-rays, so it's not a difficult detection. 16 photons in 200 kiloseconds is a solid detection. So detection-wise, it's easy.
Sure, but it's still like a 3 to 4 sigma kind of detection. to be honest.
No, it's not a 3 sigma detection. It's a very solid detection.
Oh, that was a confidence for excess above the extrapolation of the power light earlier times.
Correct.
It's
Yeah,
a different question. Yeah. What I wanted to ask, can you in any way quantify how much of a flattening you need to make this 3.5 to 4.3 sigma, say, go down to 2 sigma? How much of a flattening do you need?
Oh, yeah, like if we observe next time and we see nothing, what we would be saying, is that your question, Yoni?
I mean, right now you say you have kind of a 4-ish sigma evidence for some excess, but can you in any way quantify the excess, or it's just too hard? If you'll have, say, from t to a minus 2 point something down to t to minus 1, would it solve the problem?
Oh, like okay, no, that is way more difficult. That is way more difficult. I would have to do numbers to answer to this question. Yeah. Yeah, that's why. So I approached the problem with the simplest possible statistical question, which was, is there anything on top of it? Exactly, because any step forward adds more problems to get to an answer. Yeah.
So thank you very much.
Thank you. Thank you so much for having me.
And now it's time for our second talk by Brian Metzger on diversity of kilonova emission from binary neutron star mergers.
Yeah. All right. Very good. Okay. Welcome. So yeah, I wasn't originally planning to say much about the fallback scenario, but then I realized I sort of have to. So I have a lot of ground to cover. But hopefully, my main goal is to try to give you some idea of what theorists think would be the diversity of kilonova that would make it look different than 170817. And we may have had some opportunities to see this in 03 if we had better localization, but unfortunately we haven't had any additional joint detections yet. But I hope to motivate that some of that diversity, hopefully we'll see in 04 and going ahead. And I'm going to be very qualitative about a lot of this because the quantitative models are sort of still being progressed. There's still a lot of uncertainty, but I hope to give you the flavor of things. Okay, so one of the goals of all of this is to understand the origin of the elements. We know that the hydrogen and helium were formed in the Big Bang. The lighter elements were formed in massive stars or supernova. But as you get to the bottom of the periodic table, we know less about the origin of these elements, the R process elements, which make about half of the elements heavier than iron. And the challenge is essentially to turn iron into gold. Iron is roughly equal numbers of neutrons and protons, and gold is more neutrons and protons. In principle, it's simple. You just bombard an iron nucleus at a very high rate with neutrons, and you can turn it into a radioactive gold, which then decays to something stable and heavy. The challenge is finding a site in nature where you have a high enough density of neutrons to enable this rapid capture process. And of course, we need to go often where the neutrons are, and one such source are neutron stars. And it's particularly nice if they slam together and enable us to eject some of this neutron-rich matter into space where we can produce this R process. And one of the most striking things about 17817 that I was surprised about was how well they measure the total mass of the binary. And in retrospect, this is obvious because it's intimately related to the chirp mass for roughly equal mass binaries. So this is important to keep in mind that LIGO actually measures the total mass pretty well, and it does so in short latency. There's no reason they couldn't give us this information more rapidly, in my opinion, and it might inform some of the diversity we're going to see. So what's inside of a neutron star? Well, we're still debating what is the equation of state. We have a few diagnostics of it, namely what are the masses and radii of neutron stars. We know the maximum mass is above around 2 right now. Different equations of state, those with ordinary matter or those with phase transitions predict different relationships between radii and mass. And we're starting to hone in on these through a combination of electromagnetic and gravitational wave observations. And I'll come back to that. So the outcome of a neutron star merger is sensitive, we think, and this is based on a whole huge body of numerical relativity simulations over many years, which I can't give justice to in my citations, is a sensitive function of the total mass of the ingoing binary and the maximum mass of the single non-rotating neutron star, or you can parameterize it in such a way. So what the numerical simulations show is if the total mass is exceeding a threshold, which is about 30 to 60% above the maximum mass of a single rotating, non-rotating neutron star, the outcome is a prompt collapse to a black hole. And we think in that case, there's relatively little ejected. There is some, but not a whole lot of it. Most of it ends up in the horizon. And this happens very quickly within a matter of milliseconds. What happens more frequently is that the remnant produces a differentially rotating body, which is rotating slowly in its core, but more rapidly on its outer layers. And this angular momentum essentially temporarily stabilizes the object from collapse. But then over some longer period of time, angular momentum is transferred outward, mass is transferred inward, and overall this tends to destabilize the remnant. So after some number of viscous times or internal redistribution time scale, the object collapses. But in this case, because it's redistributed angular momentum outwards to collapse, it ends up with a more massive disk around it. And this is more, likely to give us bright electromagnetic emission. And this is more controversial, but it's even possible that if this object redistributes angular momentum in a proper way, gives enough of it to the core, and is able to come into a solid body state while still rotating at breakup, it could still be stabilized for sufficiently low mass binaries where even that object is now in solid body rotation. When it spins down, it will eventually collapse to a black hole, but now it has to do so on a longer time scale to actually remove angular momentum from the binary. And so we call this a supermassive neutron star. And it could, in principle, instead of surviving milliseconds, survive for hours or days for collapsing into a black hole. And so just a modest change, tens of percent in the ingoing binary mass for some assumed equation of state can give a wide diversity of outcome. And the name of the game is essentially LIGO and Virgo can tell us what's going in. As I said, they measure the total mass pretty well. And electromagnetically, we figure out what's going out. We see if this scenario makes sense. We see if there's phase transitions or something else exotic going on. I'm going to argue, as many people have, including one of our co-organizers, that 729.7 likely did collapse into a black hole, but not immediately. It probably went through this hypermassive channel. So here's a simulation of two emerging neutron stars. You're seeing the final stages of the inspire. What you're going to see is near the end of the inspire, the two objects tidally squeeze each other. There's matter that comes out the outer Lagrange points in the equatorial plane. Then the two stars collide together. This produces a pulsating object, which generates shock-heated ejecta, which goes out over a wider range of angles. And then at the end, we have this central object surrounded by an accretion disk, and it's losing, in this case, angular momentum to gravitational waves. And in this case, fairly quickly collapses into a black hole. But we have this torus of material sitting outside of it in this huge debris cloud by the time the black hole forms. So the type of counterpart we expect to detect these events is a sensitive function of our viewing angle. If you happen to be looking down the axis, you may see the accretion powered by this remnant disk onto the black hole. That may give you a bright cosmological gamma ray burst. If you're off axis, you may not see the gamma ray burst itself, but you might see the shock breakout of the jet through this big cloud of debris. You'll eventually see the afterglow produced by the jet and by this debris. And we've already heard Raf talk about the latest on that. What I'm going to focus on is the Kilonova. This is the thermal emission produced by the more isotropic, slower transrelativistic ejecta, which, as we heard, may also produce its own Kilonova at later times. So there are different sources of neutron-rich ejecta as a function of time after the merger. There's the matter ejected tidally, I just discussed. There's the shock-heated matter from the pulsating remnant. These are referred to as dynamical because they come out on the dynamical time scale, which is milliseconds. There's not a whole lot of this ejecta, but it does come out with a high velocity. So it would dominate, for instance, the Kilonova afterglow. More important source by quantity are the disk outflows, which are the same ones that are feeding to the black hole. These come out over seconds of timescales of seconds and can contain about an order of magnitude more mass, but they tend to have a lower velocity. And there's even an intermediate phase, which is usually ignored, which is the fact that in order, this object you produce is probably a rapidly spinning magnetar, and it's cooling through neutrinos, and this drives a wind from its surface. For the interim before the black hole forms, there could be a magnetized wind from the magnetar remnant, and this could also be an important source of ejecta in these systems. But how long this wind lasts, of course, depends on the stability of the remnant. So black holes are fussy eaters. If you try to feed them at high rates, not all of it ends up in the horizon. Although these accretion disks can cool effectively through neutrinos in the midplane, the upper regions of the disk, because of their lower temperatures, can. And so you get a thermally driven, even if you have no ordered magnetic field, you get a thermally driven outflow from the disk. So what we find, and several groups find, is about 30% roughly actually is ejected in winds, and only 70% of the torus makes it into the black hole. And the typical velocity of the disk winds is about 1/10 the speed of light. So as you have this expanding matter, either in the dynamical material or in the disk outflows, as it expands, the protons and neutrons get together, quickly form these heavy pseudonuclei like iron, but there are so many neutrons they get bombarded and form these heavy radioactive isotopes, which then subsequently decay back to stable isotopes over periods, longer periods of time. And it's the heating that's released by that decay that keeps the matter hot and produces the kilonova signal. So this is showing you the radioactive power versus time. For a single isotope, you just have a constant heating with an exponential decay, but here you have lots of isotopes which are decaying into shorter isotopes, decaying into isotopes with longer half-lives, and the net heating rate is a power law. And I encourage you to check out the recent work by Jenny Barnes, who's really quantified sort of the uncertainty in the heating rate and how it depends on the nuclear physics. And she finds there can be sizable, maybe even order of magnitude heating variations on timescales of weeks, which could impact how well we're able to determine the ejecta masses from these systems. So as this expanding matter goes out, eventually becomes transparent. This heating radiation can escape. It takes about a day for this to occur for typical parameters for the lower opacities. And then basically after that point, the luminosity is tracking the radioactive heating rate after you reach the peak, once photons can get out. And this, of course, is what we saw with 72817, matched nicely some of the existing observations. But one of the striking things about this event, of course, was the very strong color evolution, starting off very blue and evolving to become red into the near infrared. And the colors of kilonova are basically telling us about the composition of the ejecta, the opacity, because in particular, the opacity is set by a series of atomic transitions, and how complicated the atoms are will affect whether those transitions are so dense in the UV that they don't allow blue light to escape, or whether they do allow blue light to escape. And so roughly speaking, the prediction is if you just had the lighter R process elements, those at the top or middle of the periodic table, they don't have these complex atoms, these F shell electrons. And so you tend to get the lower opacity and the bluer emission, whereas if you have some of these lanthanide elements at the bottom, you get the higher opacity and you get redder emission that peaks a little bit later in the near infrared. And the key here is that the bluer redness connects to how many neutrons the ejecta has. If you only form these lighter elements if you have fewer neutrons. If you have enough neutrons, you can capture your way up and form these heavier elements. And so there's an intimate connection between the colors of the kilonova and exactly what the composition of the ejecta is. And so when we see something evolve from being very blue to being very red, it probably means we have a diversity in the composition of the ejecta, diversity in the opacity, and we probably have some complicated geometric effects going on. So one natural possibility is that the faster material that's coming out the polar direction of the merger tends to be more irradiated by neutrinos. This tends to make it less neutron rich. You have fewer neutrons, you're going to produce the lighter elements. Whereas matter that comes as shield in the accretion disk or comes out in the tidal materials, basically shielded from the strongest neutrino fluxes, will tend to have more neutrons. And so you can have a picture that was even discussed before 72817, where you could actually see both components of emission depending on your viewing angle and depending on which of these comes out first. You see the blue emission coming out and then the red emission. And this is how many groups modeled in a simplified fashion, and now has been done more sophisticated ways to infer that of the blue type of ejecta, there was about a 10 to the minus 2, a few 10 to the minus 2, moving with high velocities. And then we had the majority of the ejecta probably did have lanthanides in it, but was coming off with a lower velocity. And this was consistent with this picture. So one question you might ask with 72817 is, what was the ejecta source that produced the blue and the red components? And so I'm putting velocity on this axis and electron fraction, which is a proxy for how neutron rich the matter is. So if you're above an electron fraction of about 0.25, it means you're relatively neutron poor. You'll just produce the lighter R process elements. If you're below this electron fraction, you're relatively neutron rich, and you'll produce the heavier ones, and you'll have redder emissions, so blue and red. And the velocity, which of course we can also infer from this spectroscopy. And so you can ask, where do the different components of ejecta I mentioned earlier sit on this? Well, tidal material is very fast, tends to be very neutron rich, so it sits over here. Accretion disk outflows, depending on the lifetime of the black hole, I'll come back to this, can be blue or red. They tend to have lower velocities. The shock heated matter has higher velocities. Depending on the angle, it can be blue or red. And then the magnetar wind, because it's magnetically accelerated, it can have a high velocity, but because it's irradiated by neutrinos, it tends to have a high electron fraction. So one of the lessons from 1781, so some combination of these produce the kilonova we see. One of the obvious lessons from 1717, at least if our ejecta masses are not terribly off, is that the ejecta can't all be dynamical. This is showing you ejecta velocity versus ejecta mass, and these are from numerical relativity simulations, all these points. And so what you see is, and here is the rough error regions we need to produce the blue and the red kilonova. And what you can see is that it's possible that some of the blue kilonova was dynamical. There's enough dynamical matter with high velocity. But the redder part, the lower velocity and the large amount of mass just don't fit well with the dynamical ejecta. And they likely come from the accretion disk outflows, in my opinion. But it is important to note, and the blue component, I don't know. It could be a combination of shock heated. It could be the magnetar that's contributing to it. It could also be the disk winds to some extent. But the important thing with the accretion disk outflows is we think that its color is going to be sensitive to the lifetime of the remnant. As I said, the longer the central object survives, the more neutrinos are going to irradiate the disk outflows, which is evolving on its own time scale, about a second. And so the bluer it will become depending on the lifetime of the remnant. And we studied this several years ago. This is the distribution of the ejecta of the disk winds as a function of the electron fraction for different neutron star lifetimes. So we basically artificially collapsed the neutron star into a black hole at different points in time and saw what effects that had on the disk outflows. And what we found is, as you would expect, if there's a prompt collapse, you tend to get more of the red ejecta from the disk, but then the longer the object survives, the bluer and bluer its emission becomes to at some point where if it survived forever, it would be very hard to get any lanthanides out of the disk outflows. And this is just showing that again with some light curve models, that if you have a prompt collapse, you tend to get a stronger red component relative to the blue from the disk outflows than if you have a longer lived object. And so I think one lesson to me from 1717 is the fact that we did have evidence for the lanthanides in terms of the near infrared excess. In my opinion, it just favors a very long-lived remnant that never collapsed to a black hole. So if you go back to this story of these different outcomes of neutron star mergers, you can ask the question for 1797, which of these possibilities can we dismiss? Well, I think the prompt collapse is pretty much dismissed just because we saw too much ejecta from 17817 and there was blue material, which is very hard to produce in this scenario. I'll come back to this in a second later, but it's also difficult to reconcile things with a very long-lived supermassive neutron star. As I said a second ago, I think it would have made all of the emission blue effectively. Also, when you have a supermassive neutron star, it has this enormous rotational energy, which has to be liberated in some form before the object collapses. And we just don't have evidence for that much energy, either in the kinetic energy of the jet or the kilonova. It just doesn't seem like there's that much energy. And others, including Yanni and others, have argued along other similar lines, and also there's also some arguments related to whether you could actually get a GRB jet without a black hole forming. So I think there's a number of circumstantial pieces of evidence in 17817 went through this route. And one of the interesting things is you can turn this around and say, if I think this was the route, can I put constraints on the equation of state? So this threshold, the prompt collapse threshold, depends on the compactness of the neutron star, this 30 to 60%. And so Andy Bauswein has used that, and to some extent Radice, to put lower limits on the radius of the neutron star effectively. Whereas likewise, if you rule out a supermassive neutron star, then you can't have too stable of a neutron star. So that essentially puts an upper limit on the maximum mass. And so you can go back to this equation of state figure and ask, well, what are all the constraints we're now honing in on with the equation of state? It's quite interesting. So LIGO and Virgo are beginning to put upper limits from non-detection of tidal deformabilities. From NICER, we're hearing about lower limits on massive neutron stars, although there's still some dependence there. And then from the GW plus EM side, from 17817, we have model dependent lower limits on the radius and maybe on the maximum mass. And so it's quite, all of these limits are highly sensitive to systematics and uncertain. But I think this is the way forward. If we can do this for future events and we start to see inconsistencies, that could be very interesting from the nuclear physics standpoint. Maybe we're seeing evidence for phase transitions or something else. But let me go back to this question of how we're really sure 17817 made a black hole. So as Raf discussed, we have this X-ray emission, which is persistent and above the extrapolation of the decaying afterglow emission. And at least to my knowledge, and maybe this is changing, the radio has continued to fade. And so there seems to be an X-ray excess above the afterglow models, as we just heard from Raf at the sort of 4 sigma level excess. And she also discussed that there are these two ideas. One is that we're seeing a new component of shock emission from the Kilonova afterglow at large radii. And the other idea is that we're seeing thermal X-rays coming from the inner regions of the remnant, which is now enshrouded by the Kilonova ejecta about 3 years after the merger. So as I mentioned earlier, so it turns out that let me talk about the second possibility, the fallback scenario powering the black hole thermal emission. The dynamical ejector, there's not enough fallback. Rosvog did a study several years ago, and even under optimistic assumptions, you don't get enough. So the challenge to the fallback scenario is getting enough matter to fall back to the black hole 3 years after the merger. And you just can't do it very well with the dynamical ejector. You may be able to do it with the accretion disk winds. And so some of the first studies of these accretion disk winds were done in the context of axisymmetric alpha disk simulations with my colleague, Rodrigo Fernandez. This is a snapshot of the disk evolution about 1 second after the merger. But in order to be able to determine how much of this cloud of debris created by the accretion disk falls back to the black hole, we have to evolve this disk for many, many more dynamical times, because there's a lot of nuclear recombination and other energy being released, and the system is still sort of settling into a new state. And so this is showing you a recent paper we just submitted. This is a simulation of the fallback, which we ran for 35 seconds, which doesn't sound like a lot, but it's like 1 million dynamical times at the black hole. You couldn't easily do this with a 3D GRMHD simulation, but you can with an axisymmetric hydro simulation. And what I'm showing you here is consecutive zoomed out snapshots of the accretion flow. The red is showing you unbound debris, and the blue is showing you gravitationally bound debris. And what we found is that the early stages of the disk, which I showed you here, produce a big cloud of debris. The early outflows produce a big cloud of debris, which extends out to, radii comparable to the sun's radius. And that creates a giant reservoir of bound matter. And most of the unbound winds are coming out in the polar direction initially. They eventually get mixed into 4pi, but they're coming out in the polar. So you keep this bound reservoir, which kind of then continually falls back to the equatorial regions. Now, at these times, I'll come back in a second, but these times the black hole, the accretion flow can't cool through neutrinos, and so most of the infalling matter does get ejected. But if you wait long enough, eventually those regions will be able to cool and the matter could be accreted. So here's the punchline. We think there may be enough matter falling back. So this is the accretion or fallback rate versus time after the merger. And what you're seeing with the red line is the rate at which matter is falling back from this reservoir back to the inner accretion disk. So that's shown in red. And the black line is showing you the rate the black hole is actually accepting that mass through the ISCO radius. So at early times, the disk is able to cool through neutrinos. So all the matter that's falling back is basically being consumed by the black hole. But then after the disk drops below this accretion rate, the disk starts being unable to cool through neutrinos. And so the black hole rate starts to drop below the fallback rate. But if you wait long enough, eventually the fallback rate will drop below the Eddington rate, and now the disk can cool through photons, not neutrinos. And so we expect that the fallback rate the accretion rate onto the black hole will rise back up to match the fallback rate. And so the fallback rate, if we extrapolate it, we can, depending on the alpha viscosity and some uncertainty here in extrapolating the simulations, we find we could get within at least an order of magnitude of the X-ray excess. So it seems possible. My punchline is it seems possible that the X-ray axis could be fallback accretion. Okay, so in the last few minutes, the future is loud. We're going to see more events from different angles, different properties. I wanted to get to diversity. So as I mentioned, if you have a massive object, you expect it to collapse rapidly to a black hole. This should produce dimmer and redder kilonova emission. And LIGO's second neutron star merger, as we know, was very massive. Unfortunately, we didn't have a good enough localization to really get a deep constraint on the kilonova from this event. But if we had, we would have predicted this would have been a prompt collapse object. We also have this possibility of long-lived neutron star remnants, which now have a reservoir not just of radioactivity, but also the rotational energy of the neutron star. So this could produce brighter, faster, bluer kilonova, and maybe even non-thermal emission from the magnetar. And so the idea here is that the central remnant is now a neutron star, And so it's dumping rotational energy into the ejecta, which in addition to the radioactivity can boost the luminosity. If that energy is able to be thermalized, it's a big question. We expect that the X-rays from this nebula could become so luminous that they ionize the ejecta, and so X-rays should start leaking out at least along the low density directions simultaneous with the reprocessed optical emission. So I don't have any results to present on this, but this sounds like a lot of hand waving. And in these early works, we just had to assume a spectrum for the nebular radiation, but I'm actually working now with Indra Vroom. We've been developing self-consistent models for magnetar-powered superluminous supernova, which account for the physics of the nebula and how the radiation is thermalized. And we're in the process of applying it to mergers. So I hope to have more results for you soon. But there are some tantalizing hints along these lines. We have a recent GRB where the kilonova was 10 times higher than in 17817, and also showed X-rays that were actually strikingly similar to what we would expect for the nebular X-rays from such a magnetar. On the other hand, from the radio side, we're not seeing any evidence for radio emission, which would indicate excess kinetic energy in the ejecta of any short GRBs. So this is maybe disfavoring a long-lived magnetar. So we're getting sort of conflicting answers as to whether any short GRBs could be this. But even if these things don't produce short GRBs, this is a signature we might see. Final minute. I think the long-term game here is, the main thing I want to convey to you is that, in my opinion, total binary mass is the dominant variable controlling the outcome of a merger. The mass ratio depends a little bit on things, but it's not as, the lifetime of the remnant is everything. And as we know, the kilonova ejecta and probably the properties of the GRB jet are going to depend sensitively on the total binary mass through that lifetime. And we potentially would predict abrupt qualitative changes in the counterparts with the chirp mass as a result, because the chirp mass is essentially a proxy for the total mass if you don't vary the mass ratio too much. And so, it's important to note that LIGO and Virgo do measure this promptly. But I guess going ahead, we're going to have events, we're going to, hopefully start to see this diversity and put things into different categories. And then if we take the measured chirp mass, we will be able to iterate and figure out, okay, well, maybe where are the boundaries of these different outcomes? And do they conform to this picture? I can even imagine a future where, based on knowing in low latency the chirp mass, we make informed decisions for how to conduct follow-up. We're far from that point now. I'm not advocating that, but if we can figure out these boundaries, we're going to learn a lot about the dynamics of these mergers and about potentially the equation state of neutron stars. And so this is just rehashing that basically we are trying to create a matrix which connects the gravitational wave chirp mass to the electromagnetic signature. And if we start filling out this matrix and it doesn't make sense with what our relativity simulations are saying, then we're missing some physics, and that's important. So this is just a framework for thinking about this. Okay, I'm basically out of time. So I didn't have time to talk about all the different things. I hope I conveyed to you that although we have this sort of general picture of mergers, some or all of these different signals will exist in different strengths depending on the mass going in. And so I think it's really going to be exciting over the next decades, hopefully next few years, as we really break down this diversity. Thank you.
Thank you. There isn't too much time for questions, so are there any urgent questions? If not, I can quickly ask, how strong, in your opinion, is the evidence against prompt collapse to a black hole, and can it be circumvented?
I think it's very hard. If you collapse to a black hole promptly, then you have no source of neutrinos, and so all the ejecta should just be basically neutron star material, and it all has a very low electron fraction, and you basically ubiquitously produce these lanthanides. And I just think it's really hard to explain the UV colors we saw at the early phases of 17817.
With dynamical ejecta on the one hand and disk wind on the other hand,
well, yeah, the disk winds. Yeah, I think the disk winds are not going to. there's not going to be, because you make very small disks when you have a prompt ejecta, and so the disks don't make a lot of neutrinos. So yeah, I think it's hard. I don't know how you get the quantity of the mass, and I just don't know how you get a massive enough disk to irradiate the matter with enough neutrinos. So I don't want to say never is never, but there's lots of weird things you can do with oscillations of well, I don't even know how that would help you in this case. Yeah, my view is it's very hard, but I'm relying a little bit on the outcome of what numerical relativity simulations say. So
exactly, the question is, if you put in more physics, etc., could you change this and so on? But yeah, that's probably a question for
I think if we can change the radioactive heating rate enough, maybe, but I think it's overall very.
Right, there's a raised hand, so quickly, if you may.
Hello, thank you for this very nice talk. I would like to ask about how reliable are simulations when, for example, we can obtain the ejected mass in a binary neutron star merger, and how can we link that to the original density structure in a neutron star? I mean, for example, if we have ejected mass of 10 to the minus 2 solar masses, can we link that to being ejected from the crust of the neutron stars? Or, I mean, are simulations reliable on this step?
I don't think I've never seen it expressed that way, where they try to connect back what part of the star is ejected. But the matter is so processed by the time it gets out. I mean, it very rarely stays cold. It gets shock heat, so it's basically heated up to nuclear statistical equilibrium. So I don't know if its actual origin in the star.
Yeah, because I think that there are some works by Andy Baswing and some other people, I think, that they were able to sort of follow the flux tubes of matter some years ago, and maybe it was 2017 or before, and they were trying to make the argument that essentially the core of the both neutron stars are so bound that essentially the matter that is ejected, I'm not talking about what happened next of all the processing, but the original amount of mass, the amount that is ejected, could be linked to the low density part of the neutron star equation of a state. So I was curious to see if simulations have evolved or they have looked into this more deeply.
I don't know if anyone's looked into that more deeply. I mean, you have to go, if you excavate down to 100th of a solar mass in a neutron star, I don't think you're yet probing the. So I don't know on that point.
Okay, thank you.
And with regards to the ejecta mass, how much we can trust them from simulations. I mean, there are groups that have done tests. I mean, they don't agree. They tend to have disagreements at the factor of 2 level, like where they run the exact same binary with different codes. But there is now some convergence on ejecta mass in the community. What people disagree more is the composition and the rate of transfer of neutrinos and things. But
thank you very much. And we really have to go to the next talk because we're running a bit late. Sorry. Okay. So thank you very much. And the next talk is by Ramandeep Gill, also known as Sunny. Emission from structured GRB jets, theoretical overview.
Sorry, I was having some trouble switching my mic back on after sharing the slides. So let me try again. Just a second.
Sure.
Oops. Let me try again. All right. Okay, I hope you can see my my screen here. Great. So thank you so much for the invitation to talk about this very interesting topic, which is emission from structured GRB jets. And we've heard a lot interesting things from Rafaela and Brian already. So I've divided this talk into two parts: prompt emission and afterglow, where I'll be discussing a few different topics. For namely, from prompt emission, suppression of emission for off-beam observers, and I'll tell you what off-beam means, compactness constraints, shock breakout emission. Moving on to afterglow, what do you expect to see for off-axis observers from a top hat or a structured jet? I'll emphasize in the end the three diagnostics that are important to distinguish between different jet structures, such as centroid motion, image size, polarization, and how something else I'm very excited about, the last topic, how linear polarization is such a useful tool to constrain the anisotropy of the shock post-shock magnetic field structure. And in between, while I'm discussing these different concepts, I'll pull out some examples and how these different concepts were applied to understand the structure for GW17.17. Okay, so I'll start by asking the question, why consider any structure in GRB jets when you do have this simple model of a top hat jet? And I'll remind you what top hat jet means. It's just a uniform jet with the properties such as the energy per unit solid angle and the bulk Lorenz factor of the material are uniform, and then they cut sharply at some angle theta j, as shown here. We all know, and you can see from the cartoon as well, this is such a simple and idealized model, but it has been instrumental in determining many of the fundamental properties such as the afterglow, linear polarization, and many other things over the past several years. And it was, initially strongly supported by observations where it was predicted and then subsequently observed. This achromatic jet break that you expect when the ejector slows down, where the bulk Lorenz factor goes down to 1/theta j, and then the observer sees this sharp steepening in the afterglow light curve, indicating that the observer has now seen the edge of the jet. And so those works were instrumental in constraining the total energy that is actually emitted in the emission, given that we only observe E gamma ISO, and that is constrained by this beaming fraction factor, multiplicative factor, which is just simply the ratio of your solid angles, delta omega over 4 pi, scales of theta jet squared. And so these sort of arguments were used to constrain the total jet energy, and also to constrain the number of events that you should be seeing after accounting for this beamed emission. When observations started pouring in, we had more collected data or looking at the jet breaks from several of these GRBs. It was realized that there is a lot of scatter between the E gamma ISO and the theta jet that we see. So attempts were made initially to sort of unify this model into a universal structure of angular structure jet, where now we have angle. The energy per unit solid angle is distributed in some fashion, for example, a power law to the power law index minus a as a function of angle. And similarly, the bulk Lorenz factor is also distributed, theta to the minus b, where theta scales approximately like this. There could be other models than power law jets, for example, Gaussian. And so attempts were made to sort of unify this scatter in theta j and E gamma ISO into something that is universal, with the jet having a constant energy budget, which sort of reminded, resembled the same idea that was used in AGMs, where you're seeing a single object from different viewing angles. So all the scatter that was coming in would just be due to the different viewing angle of the observer. And one of the popular models for this universal structure was universal structure jet, where A was set to 2 and B was 0. And the reason why it was popular, because it was able to produce very similar afterglow light curves, and also the jet break that was seen for a top hat jet, where theta jet in case of a top hat jet would be replaced by theta observed when the Lorenz factor of the ejector would slow down to 1/theta observed. You would see a similar jet break. But it did have some problems, and it didn't agree with many of the observations. They're highlighted in this paper, Nakar 2004. But now we're much more well informed, where several groups have conducted 2D, 3D hydro MHD simulations of jets breaking out of a confining medium, where for long duration GRBs, the confining medium would be the stellar interior of Wolf-Rayet stars. And when discussing short GRBs, such as today, the confining medium, as we heard earlier, would be the dynamical ejecta that you have after the merger of the two neutron stars. And now we have a much more complete picture from these simulations, which tell you that the angular structure is a a natural outcome of the interaction of the relativistic jet that's launched with its surrounding, which is the confining medium here. So I pulled out several examples, such as this from Davide Lazzati's group, where the jet is interacting with the subrelativistic dynamical ejecta, and how it forms this wide angular structure where both the energy per unit solid angle and the bulk Lorenz factors are distributed over a wide range of angles. Similar things are found when you have MHD simulations, where you do see similar distribution of the energy, although there is, when you look at more closely, there is a hollow core due to the magnetic field pushing the material out for MHD simulations. And here's another example of a hydro simulation done in Gottlieb et al., where they've tested different types of injecting different kinds of jets and changing different model parameters. But there's some sort of universal picture that is emerging. So for these three different models that they show here, there is some universal structure that you see, which resembles very much like a power law jet, and it is quite different from a Gaussian jet. Okay, and similar things can be found for the velocity distribution of the ejector. So let me move on to the prompt emission and tell you about how it is different from on-beam and off-beam observers. Now, all of you are familiar when you have relativistic ejecta, the emission that is produced in the co-moving frame, be it isotropic, it is strongly beamed in the forward direction due to the aberration of light effect into a cone of angle delta theta 1 over gamma. So any observer that is any observer is receiving an on-beam emission if that observer's line of sight is passing within the beaming cone of that emitter. So anybody looking down the barrel of the jet, or even just outside, but if the line of sight is passing within the 1 over gamma beaming cone, would be on beam. Anybody who's outside would be considered off beam. So this has important implications of how the emission and the peak energy is suppressed. So that just simply comes from the Doppler beaming. So for example, the energy of the peak emission would just simply be the Doppler factor times the co-moving peak energy, which is simply this, which scales as a function of the angle theta twiddle. And theta twiddle is just the difference in angle between theta observed and theta naught, which I call theta twiddle here. And how that scales when you're on beam and off beam. So certainly when you're on beam, you're getting the full emission. There's no suppression there. So A, which is the ratio of the off beam peak energy to the on beam, is unity. And as the observer becomes off beam, that scales down with gamma theta twiddle as to the -2. Things are a little bit more complicated when you have when you try to constrain or understand how E gamma iso scales down with theta twiddle. And then those effects I show here, again, for the on-beam, it's unity. But as you go outside the beaming cone, but not too much outside, it scales down as gamma theta twiddle to the -4. And there's a very large suppression if you go far away out, when theta twiddle is much larger than theta naught, for example. You basically go into the point source limit, where the suppression is massive. So now when you have these scaling relations, they can be very useful, given that you can constrain these two ratios, the E peak ratio and the E gamma ratio for on-beam and off-beam observers. And that's what we did when we learned about the very underluminous nature of the hard initial pulse that was emitted for GW1717, as shown here in this very nice plot from Rafaela's and Ryan Cornock's review article. And it sits far off from the distribution of other short GRBs that we had seen in the past. So if we apply what I showed you on the previous slide, those concepts where we have some constraint over the E peak and the E gamma iso. For example, if what we're observing is much smaller compared to what the on-beam observer would have seen, for example, by a factor of 10 to the -3 or even 10 to the -4, assuming that the ejecta is highly ultra-relativistic, then we would come to a conclusion that the on-beam observer would have seen the E peak of the emission, which is much harder compared to what you would understand by looking at the distribution of short GRBs that we've seen already. So it would be much harder, 6 to 20 MeV, which is unlikely. Okay, so one of the implications for this result was that we are in fact observing on-beam emission but the observer is off-axis in this, and it's very different from a top-hat jet where we don't have any off-axis material, but now there is material sitting along the line of sight that is emitting towards our direction. So some of these ideas can be put together in a structured jet outflow model or a cocoon shock breakout model, as was discussed in some of these works. There are important constraints that can be placed due to compactness of the region that is emitting the prompt gamma ray emission. So compactness is simply a measure of how likely photons that are emitted above the self-annihilation energy, which is just simply MEC squared, how likely they are to pair produce and go through gamma-gamma annihilation. So for a test photon of energy x sub t, and x is simply just the non-dimensional energy E over MEC squared, and that test photon would annihilate with photons of energy that are higher than this threshold. And then to put together a simple measure of compactness, we can just simply look at the isotropic equivalent to luminosity that are emitted in gamma rays, given that a large fraction of that energy is emitted above the MEC squared threshold. So it's simply just for our 4 pi r square c times the energy density of the radiation field boosted to the engine frame. Putting this together into this compactness parameter, we find that the emission is for the typical parameters that we have for GRBs, in the co-moving frame, it is highly compact, which means that we will end up producing a lot of pairs. So another way of putting and understanding this compactness is that this is equivalent to the opacity to gamma-gamma annihilation modulo this factor F gamma-gamma, which is the fraction of photons that can actually pair produce. And this is what's the standard practice in the field that's used. And we know this from a detailed work done by Lifik and Sari, where they calculate this tau gamma gamma based on assuming a power law photon number spectrum with index B. And you can see it has a high dependence on gamma. Beta is usually -2 or so. So tau gamma gamma goes as gamma to the -6. And the impact of that is that if you, for example, I'm showing you here, if you have a spectrum with, emitted by a relativistic material with gamma of 200, if you reduce gamma 200, and all of the high energy emission will be highly suppressed because it'll be optically thick for the photons to get out. So this concept can be applied to understand what is the minimum Lorenz factor, given you can set tau gamma gamma to 1 and ask if you see a cutoff in the spectrum, such as here, or the highest energy photon that you see for a given spectrum, what would be the Lorenz factor? So we know all this from the standard practices in the field. So what happens when you have structure? So how does that the compactness limits change? So I'm assuming the same power law structure jet as I showed you earlier, and this is a plot of the optical depth of the pairs that are produced after photons annihilate via gamma gamma, and shown for different values of this power law index parameter A and B. And what you see here is that for the red curve where B is set to be 0, you're not much affected by any compactness constraint. So when the jet structure starts to develop steep gradients in the bulk gamma, you are very much affected by this ratio, or beyond basically the core of the jet, you are highly compact and you will not see any emission. So similar results were obtained in work by Paz Beniamini and Nakar 2019, where they applied different arguments looking at the distribution of the energy ratio emitted in the X-rays compared to the gamma ray emission energy, and they constrain this angle theta gamma, and they arrived at the same conclusion that basically when you have steep bulk gamma gradients, you are very much limited to emission coming from the core and not much outside of it. Similar ideas were applied for the emission for the hard spike that we saw in GW17 in Matsumoto 2019, where from the gamma-gamma constraint, the compactness constraint that I discussed, they were able to constrain the gamma minimum Lorenz factor for the material that emitted the hard spike to about 5. Okay. One of the other emission components that is expected when you have a relativistic ejector trying to come out of a confining medium is when the relativistic jet and the accompanying cocoon drives a strong shock into the confining medium. So for short GRBs, that would be the dynamical ejecta, as shown here, an example from Cassidy-Wall 2017. In such shock, the dissipation is radiation mediated, and the energy and the pressure behind the just after the shock and the shock downstream is radiation dominant. And for those reasons, these shocks are also referred to as radiation mediated shocks. So when the shock actually breaks out, for example, from this direction here, you see a burst of gamma rays that are trapped behind the shock, and then which is followed by something that's referred to as cooling emission, where radiation from deeper parts of the flow, optically thick part of the flow, continues to leak out over much larger time scales. So here's a schematic of what to expect when you have such radiation-mediated shocks. So in the frame of the shock encounters the upstream medium at the velocity of the shock, which is slowed down immediately in this immediate downstream region to something very non-relativistic. And also shown here is the temperature of the material as it enters the shock. It rises in the immediate downstream region, and then it cools as it becomes more and more optically thick, going more and more downstream. The temperature of this is what's released when the shock actually breaks out. So the temperature of this radiation is limited by production of pairs, and it is constrained to be between 100 and 200 keV or so. So this is what you would expect to see if there are not a lot of pairs when the shock breaks out. But if there are pairs, the shock expands and adiabatically cools. So you expect to see something like 50 keV multiplied by the Lorenz factor of the shock. Okay. And the time scale of this sort of emission is determined by the radial or angular time scale, which goes like R over 2 gamma square C, and it could be of the order of several seconds. Let me move on to the afterglow. So if you are an on-beam observer, basically looking down the barrel of the jet, what you initially see is declining afterglow emission, and that's is demonstrated here in this figure from Yoni's 2002 paper, shown for two different approximations, whether taking the approximation of a point source or a top hat jet that is also undergoing some lateral expansion. These are the solid curves. So as an on-beam observer, you would see emission as if it's coming from a spherical region. It would be declining until you see this steepening, as I mentioned earlier, which is the jet break, when the observer is made aware of the edge of the jet, and that is when gamma becomes 1 over theta naught. And the time scale of this jet break scales quadratically to theta naught, as we saw earlier. When you're an off-beam observer, which is simply here, you see rising emission, very much different from the on-beam case, until you see the core of the emission. So basically, the ejecta has to slow down. The beaming cone widens over time, and then the beaming cone, when it starts to engulf your line of sight, that's when the light peaks. So basically, when the Lorenz factor of the ejecta becomes 1 over the difference between these two angles, theta observed minus theta naught, the edge of the jet. And again, the peak of the emission for these different angles scales with theta observed square. This is for semi-analytic models, but when you try to do hydro simulations, you find that this steep rise to the peak and the width of the peak is not as narrow. That is because when you have an initially top hat jet, when you do this hydro simulation, you find that within 1 or 2 dynamical times, you see this bow shock type of structure develop, where you no longer have this fast-moving beam jet, but you have material, much slower moving material, which forms this bow shock, and the velocity vectors are not pointed in one direction, they're pointing much more sideways, and that's the reason why you see emission which is much more shallow compared to what you would expect from what I showed you earlier from a semi-analytic model, where the emission rises very steeply. Okay, now the question is, was this enough to explain what we saw, the shallow rise that we saw in GW17 or 17? And when we compare results from such a hydro simulation, we find that the answer is no. An initially top-edge jet lacks the complexity and the requisite angular distribution of material needed to explain this shallow rise, but it's not a complete failure. It is a useful tool to understand the behavior of the light curve near the peak and also post-peak evolution. And many of the things can be, for example, the energy, the ISM density, and many of the micro physics shock parameters can be constrained to some extent, although there are many degeneracies, as Rafael also pointed out. But one of the things that can be constrained quite nicely is this ratio theta observed over theta naught. Okay, for this particular case, we were able to constrain it to 3. Other people who have done simulations of structured jets, they find typically this angle, this ratio is of order 4 to 6. And there's a nice discussion of that, and all of these things have been compiled in a nice table that you can see in this work. Now, this is important. The point I want to make here is that there is still enough degeneracy that we cannot break this. So we need another way to another indicator to break the degeneracy between theta observed and theta naught. Okay. So just by doing light curve modeling is not enough. Of course, when we try to model the emission of GW17 and 17, the afterglow with structured jet models, for example, a Gaussian jet or a power law jet, we can very beautifully explain this shallow rise that we saw. And I'm also showing you from a semi-analytic calculation what you would expect compared to what I showed you earlier from a hydro calculation, what you would expect for a top-edge jet, and you can see it fails miserably. Okay, so you have to have angular structure, as we learned from GW17 and 17. Moving on to what you would expect and how things are different when you have a structured jet and how the afterglow is different in such a case. One of the major differences is that the observer is never off beam. You're always on beam. So you're always getting emission along the line of sight and much smaller angles up to theta min. These are the smallest angles that are beamed toward the observer, and they evolve over time as the ejecta slows down. So here I'm showing you the evolution of such an angle theta min for the two jet structures, Gaussian and power law. And then you see that at early times, theta min is steady, doesn't change until the material which is sitting at theta min naught starts to decelerate significantly. And then the observer has access to emission coming from smaller and smaller angles towards the core of the jet until you reach until theta min reaches theta core, and that is when your afterglow light curve actually peaks. Okay, and this depends on properties of the ISM radial distribution and also the angular distribution of the energy. So this is one way to constrain such parameters. And so here's an example from recent work that we did with Paz and Yoni, which shows you for one particular distribution of the energy. For example, A, which is here, is 4, and B is 2. And what kind of light curve you expect in such a scenario? So this is a very generic sort of setup here. And on the side, I'm showing you the angle from which most of the emission is coming towards the observer and how it changes as a function of time. So the jet axis in this picture it's here, and the viewing angle, the observer's line of sight, is here. So initially what you see is rising emission as what you saw in the previous case in the top edge jet until the material that is sitting at theta observed, the material that is emitting towards you, starts decelerating. Okay, and then it follows this post-jet break spherical sort of evolution that you expect for an on-axis observer or on-beam observer until the point when emission from lower angles, which is shown here, and how these contours move towards the jet symmetry axis, when emission from the lower angle starts dominating the emission coming to you, then you see this again, there's a rise to another peak until the point when the observer sees the entire core of the energetic core of the jet, and then the light curve sort of simply follows the post-jet brake evolution. Okay. So there are, given the exact structure of your flow and the observer viewing angle, there are a variety of light curves that are possible. I showed you this example, but you can also get something where you don't have this dip, but you have this only single peak and no peak here. And then there are other various types of light curves that you can see given the exact structure. And I think Paz Beniamini will discuss this at length in his talk, so tune in on July 9th when he talks about this. So in the last 5 or 6 minutes that I have, I want to discuss some of the diagnostics that I promised earlier. So when we saw this initial rise of GW17877 afterglow emission, there was a lot of confusion of whether we are looking at a structured jet or whether it is emission coming from a wide-angle cocoon type of flow. So these are pictures from Kunal Mooley's paper. So here's a structured jet, and here's something what you can expect in many cases where the jet is not strong enough to penetrate the dynamical ejecta and it is in fact choked. So there the emission would come off from this wide-angle outflow. So initially, and several in the flurry of papers that followed after the discovery of this event, people tried to model this with different jet structures and also cocoon type structures. And we were nicely able to explain the early emission up to the peak in all of these models. But these type of cases we will also see in the future. So I want to discuss a few diagnostics that can be used to discriminate between these two cases. And one of the things that was very useful is flux centroid motion. So this is coming from the semi-analytic calculation that we did. And we found that for the two structured jets, the Gaussian jet and the power law jet, you expect to see a large flux centroid motion over any given amount of time compared to what you would expect from any quasi-spherically expanding flow, which is the green line here. And this was nicely verified, this fast motion that you expect from a structured jet when Kunal Mooley published these results from radio VLBI observation, where over a period of from 75 days to 30 days, they found a flux centroid motion of 2.7 milliarc seconds. We didn't, of course, hit the mark because our results were published much before Kunal's result. But the point here is we were in the ballpark. And the expectation that you do see fast motion was nicely verified, and it sort of disfavored right away the result that we're seeing emission from sort of a quasi-spherical flow. And of course, we knew the distance to this object, so we were able to verify the apparent velocity on the plane of the sky, which is 4c, the superluminous motion, which is a smoking gun and a telltale sign of a relativistic narrow core. And we're seeing the emission from such a narrow core. Okay, the other useful diagnostic that can be used, which also came from our semi-analytic calculation, is the afterglow image size that you expect from different types of outflows. So from the structured jets, as shown here, and from the quasi-spherical outflow. Now, it is a bit hard to distinguish between the two because they're very much close together, but only at later times you can have some idea between some power to distinguish between the two. But even here, if the image is even marginally resolved, which was the case, and these are observations from Giancarlo Ghirlanda, where they're able to constrain the source size to 2.5 milliarc second with 90% confidence around 207 days, which nicely agreed with what we expected to see from our results. But even a more stronger discriminant here is the axial ratio that you expect from different type of structures, and the ratio from a structured jet is much larger compared to a quasi-spherical naturally. From a quasi-spherical flow. So this can be a very useful tool to discriminate in future such events between the different structures. And finally, I want to get into how we can use linear polarization to constrain the post afterglow shock magnetic field structure. So once you've modeled the light curve and the flux centroid, you know the angular structure of the flow and you know the viewing angle quite nicely. And that can be used to constrain the anisotropy of the magnetic field. So many of the theoretical and numerical works find that the magnetic field is generated post-shock via this two-stream instability, and it is very highly anisotropic, meaning that it lies in a plane transverse to the shock normal at all places. The field is generated at very small length scale, the electron skin depths, and compared to the emission region behind the shock that is giving you the afterglow emission, it is much smaller. So there's a large separation of scale. So the initial worry was whether this would be able to survive over such long scales.
Sunny?
People have done a lot of PIC simulations. Yes.
Your time is pretty
Hello?
much up. Sunny?
Yeah, so I'm just finishing up. So people have tried to use, so we can use linear polarization to constrain the anisotropy of the field. And I'm just trying to finish very soon here, don't have much time. And we try to do that given that we had an upper limit on the polarization. We try to constrain, it's a useful constraint for the outflow structure as we found. And we were able to constrain the anisotropy of the magnetic field using even this upper limit. And I'll have to skip this slide and go straight to my conclusions. So I was able to show, I hope to you, that GRB jets have angular structure and are not completely simply top-edge jets, but they're much more structured, as we learned from many of the simulations. The initial top-edge jet is useful to understand the light curve behavior near the light curve peak and the post-peak evolution of the afterglow. The semi-analytic models that we use to understand many of the outflow properties are again a useful tool, but there is a need to develop models that can understand the trans-relativistic regime, as most only assume the relativistic regime in doing such simulations. The shallow rise that we saw in GW17 at 17 could be explained both by a wide angle, the initial rise at least could be explained by both a wide angle quasi-spherical flow or a structured jet. And of course, we learned about the differences between the two from the Flux Centroid motion that was observed. I talked about the 3 diagnostics. These are very useful tools that will become effective in future events. And the linear polarization, I didn't get much time to talk about it, but it is something that it's such an important tool that can be used to constrain the anisotropy of the afterglow magnetic field. So I'll stop here. Thank you so much for listening.
Okay, thank you so much. We're over time. There is no time for questions. Anything urgent, please write in the chat. So the next talk is by Kunal Muli. Okay, please.
Sorry, just getting set up here. Give me one moment. All right, is everyone able to see my screen?
Yeah, we can see your screen.
Now.
Okay, excellent. All right, so hello everyone. Thanks to the previous speakers of this session for providing a nice overview of the Kilonova and Afterglow emission from neutron-star mergers, and especially from GW170817. So my talk focuses on the Afterglow emission and will be pretty straightforward. I'll cover 3 basic themes. First, the ejector morphology and Hubble constant from GW170817. I'll go on to addressing the late time excess, and finally the future prospects for the LIGO, Virgo, and Kagra detectors. So let me first begin by pointing out that the afterglow of GW170817 has been observed by 10 different telescopes, over 10 different telescopes across the radio, optical, and X-ray wavelengths to produce this spectacular pan-chromatic light curve spanning 4 years since the merger. As we have described in the paper led by Svi Makatini, that we've tried to present a uniformly processed data set, which is This recently revised and up-to-date data set is available online on GitHub at this URL. So just something to keep in mind. All right, so the afterglow light curve is consistent with a simple t to the 0.9 rise, a peak around 150 days, and a steeper t to the minus 1.9 decline in the light curve. And as Ramandeep already indicated in his talk, the shallow rise came from the cocoon or the wings of the structured jet, and the steep decline came from the jet core. So now this shape of the light curve, as has already been alluded to, gives us some important information about this observing angle, theta obs, and the jet half opening angle, which is the theta jet. So just to remind you, for an on-axis jet, we expect to see a monotonic decline in the light curve. But in the case of GW170817, we actually saw a rise followed by peak and a steep decline, which points to a jet that is seen off-axis. And the sharpness of this peak gives us an estimate of the ratio of theta obs to theta jet, which in the case of GW170817 is about 5 or 6. And the light curve itself is not able to give us any individual measurements of theta obs and theta jet. So in order to break this degeneracy, we need to rely on an independent measurement, which came from the radio VLBI through the detection of superluminal motion. And the radio source associated with GW170817 moved by about 3 milliarc seconds. This has already been covered in the previous talks, and this implied superluminal motion at 4 times the speed of light between 75 and 230 days. And what this gives us is a measurement of the Lorenz factor, roughly speaking, of the jet core around the peak of the afterglow light curve, or about 150 days after the merger. And with these two measurements, one from the light curve and the second from the VLBI proper motion, we can calculate theta obs and theta jet individually. So a more detailed procedure using hydrodynamical simulations shows that the full permitted phase space that the jet, what the full permitted phase space is, allows for a theta jet, which is less than 5 degrees. And a theta obs, which is between 14 and 28 degrees. And the sort of image to the left is showing you here the outflow structure from the hydro simulation, the best fit model, and the cartoon representation to the right. And this plot shows you the jet angular structure for the best fit model that fit the VLBI as well as light curve data perfectly well. All right, so under the assumption that the jet axis is now aligned with the axis of the binary neutron star system that merged, we can use this tight constraint on the geometry to obtain a standard Siren measurement of the Hubble's constant. And the plot here shows you the posterior distributions for H0, the orange curve showing you the gravitational wave signal used together with the EM localization, and the blue curve showing you the additional sort of information that the afterglow light curve and VLBI proper motion gave. So it shrinks the uncertainty in the Hubble's constant in the standard Siren measurement. And the inset shows you here that with more such mergers, we will be able to reduce these uncertainties. Now, this is just 1 over square root of the number of mergers. But with roughly 15 such mergers similar to GW170817, we can possibly resolve the discrepancy between the Planck CMB and type 1A measurements, type 1A supernova measurements, I mean. So however, to achieve this precision, really we'll have to rely on mergers that are located within about 80 to 100 megaparsecs, at least initially. Over the next decade or so, I think within a decade, I think this scenario will change, but at least for now, we're limited to like 80 to 100 megaparsecs. Okay, so let me move on to the late time afterglow excess seen in GW170817 that Rafaela gave a nice introduction to. The afterglow is currently very faint, and practically only 2 telescopes, I believe, are capable of detecting it. One is the VLA in the radio, and second is the Chandra in the X-rays. And so we obtained a very deep observation of this of GW170817 with the radio using over 40 hours, including a small some fraction from Rafaela's program. taken around 1200 days post-merger to achieve sub-microjansky sensitivity. And this is one of the deepest images actually produced with the VLA. But nevertheless, using different imaging techniques, now since this is so much at the detection threshold, using these different techniques, we consistently find an emission at the 3 sigma level here, shown by the white circle. And so our measurement at 3 gigahertz, so for the flux density, is about 3 microjanskis. And plotting this together with our broken power law model of the afterglow light curve, we see that this yellow data point is in good agreement with the simple model and does not indicate any excess emission. However, if you look at the X-ray flux density at plotted at 1 keV here, the data point in magenta, it shows a curious 2 to 3 sigma excess. Now, I should point out here that the X-ray flux densities are calculated by fixing the photon index, X-ray photon index that is used to calculate the fluxes, go from raw data to the fluxes, according to the spectral index that has been implied by using the full multi-wavelength data set, right from radio, optical, and to X-rays. So now if we really recalculate the X-ray fluxes differently, starting with the raw X-ray data by leaving the photon index as a free parameter, that is shown here, and plot the resulting flux densities at 5 keV, then the excess that was seen is no longer significant. And I can flip back and forth a few times to see how the magenta X-ray points change based on the differences in the X-ray parameters like X-ray, like the photon index and frequency. So this is at 1 keV where the photon index is fixed. This is at 5 keV where the photon index is a free parameter. Again, 1 keV, you can see the excess, but in 5 keV, it's no longer substantial. So really what this shows is that the observed fluctuations are most likely statistical in nature, and there is not significant evidence of this late time excess emission. However, I do believe, and it's going to be interesting, that continued monitoring of the afterglow, as already Rafael alluded to, will be very useful for finding any new afterglow component. And one of the interesting possibilities is, of course, this collision between the dynamical ejecta and the ISM, which can produce this new component, as has been introduced again by Rafaela. So the ejecta can be modeled as a power law profile in kinetic energy. And this profile is sensitive to the neutron star equation of state. And these different colored curves from Aprajita Hajela's nice paper that Rafaela alluded to very often is shown here, these different profiles obtained with these different equations of state. So from the late time radio data, we find no new component, and hence we can rule out the profiles that are shallower than gamma beta to the -5. That is, alpha needs to be larger than 5. And this can be compared with the value that is from the Hajela 2021 paper, which suggests alpha maybe between 4 and 6. Under the premise of an X-ray excess. And the afterglow models here have been sort of calculated from Aditya and Katim Gamaraju's 2019 paper. Okay, so I would like to finish up with a couple of slides on the detectability of radio afterglows. First, the detectability of proper motion, just because it is so important in breaking this degeneracy and getting a precise measurement of the observing angle. So this plot is showing you the observing angle versus the density in which the mergers take place. And the color coding is the detectable distance for a 5 sigma measurement of the proper motion. And so really for most of the mergers that are within 75 to 100 megaparsecs, the proper motion measurements will be quite possible, quite feasible. The detectability distance is somewhat larger for brighter afterglows, but smaller for mergers that are more edge on. And for GW170817 that has been shown here with the star-shaped symbol, has a proper motion detectable up to 80 megaparsecs, given a reasonable allocation of time on current VLBI facilities. But this slide really tells you the detectability of afterglows themselves with current facilities on the left and with future facilities on the right. So here the observing angle is plotted as a function of the detectability distance, and the gray shades denote the detector range for various gravitational wave sort of stages of operation for the detectors, meaning O4, Voyager, and so forth. And these colored curves are showing you the densities of the environment densities for these mergers, which determine the peak flux density, peak luminosity, basically, of these afterglows. And I think generally with current capabilities, we see that GW170817 like events can be observed up to about 100 or so megaparsecs. But this will rise to a few hundred megaparsecs once over the next several years, once these facilities like the next generation VLA, SKA especially, will start to come online. So of course, I mean, with mergers that are more edge on, the jet afterglow itself is going to be quite weak. But if they occur in more dense environments compared to GW170817, they'd be much brighter and detectable to much further distances now. Here again, this is assumed that the search is across a blind search across a 10 square degree localization region. But if arcsecond localization is available, then the distances are much, much larger. And I would like to just mention that these future facilities that are going to come online over the next several years will have these VLBI capabilities, meaning the telescopes themselves will perform VLBI observations by default, right? So any observation with these telescopes will be a VLBI observation. And that will stretch this range, the detectability distance up to which we can do VLBI. So this will be quite interesting. And so I will end by saying that in 04 and beyond, the Jaguar collaboration will continue to provide a comprehensive radio follow-up of gravitational wave events using a suite of telescopes across the globe. So thanks for attending this session, and I'll leave you with the summary and happy to take questions and comments.
Thank you very much, Kunal.
Yeah.
I see that Rafaela has her hand up. So please,
please go ahead.
Yeah, so I want to reiterate that the statistical significance can only be computed in a Cambric phase space, and that comparing things at 1 keV or 5 keV or whatever energy you want is not the right way to do it. I hope that your fluxes are not corrected for the right PSF correction.
They are, yeah.
We were off of 30–40%, right?
Yeah, that's
but
great.
My question is another one. So in the paper by Balasubramanian, the radio data point is never presented as a detection. It's always presented as the peak flux in 1 pixel within the beam. So, and the author themselves never say detection. And when I talked to Alessandra, she never said detection. So my question is, why are you treating this as a detection? What's the rationale?
Well, it is just the emission within at that location, basically. So that's all. I mean, if you believe a 3 sigma source, then that's what it is. So whether you want to call it a detection, it's its own personal choice, but we decided to go a more conservative way, that it is a 3 sigma emission. So that's what it is, and that's what we quote.
Okay, certainly this is a very interesting topic, but we do have to move on, I'm afraid. So let's thank Kunal again. And our next speaker is Masaki Mori.
I'm going to stop my share screen. 1 moment.
Hello, this is Masaki Mori from Ritsumeikan University, Japan. And this is a talk from the experimental side. I'm talking on the CARET search for gamma ray counterparts of gravitational wave events. Sorry. Oh, and this is the list of name of the CARET collaboration. These scientists come from Japan, Italy, and the USA. And this is the CARET payload. it was launched in 2015 by the Japanese H2B rocket and installed on the Japanese experimental module exposed facility. And it is operational since then. Our data are available just after the first event of the black hole merger. And there are two instruments on board the CARET, and main detector is a calorimeter to measure charged cosmic rays. And another is the CARET gamma ray burst monitor. The main detector, CARET calorimeter, is a fully active thick calorimeter of 30 radiation lengths. And it is optimized for electron spectrum measurements well into the TeV region. And this is a cross-section about detector. And from the top, there is a charge detector. And then the imaging calorimeter, which we call IMC. They track particle tracks. And then the total absorption calorimeter, which we call task. It absorbs all the shower energy to measure the particle energy precisely. And this is a thick calorimeter, and 1 TeV electron shower is completely absorbed by this apparatus. And I do not talk the results from the CARET gamma ray burst monitor, but it's there's two hard ray X-ray monitors and one soft gamma ray monitor is on board. And please refer to the Kawakubo-san's talk to be given at the International Cosmic Ray Conference next week. So CARET is on the International Space Station, and the ISS inclination is 51.6 degrees. So it never goes into the North Pole and South Pole region, and our observation is limited in this range. But still, there are some effects for the North Pole region and South Pole region, and also there's a South Atlantic anomaly in the South America. So our event trigger rate differs on magnetic latitude. Say trigger rate is high for South and North, and then South Atlantic anomaly. That means there are more background in that regions. So CARET calorimeter is basically a charged particle detector, but we can distinguish gamma rays from charged particles by our apparatus. First, gamma rays are selected by they are having charge zero. I mean, the top detector, CHD charge detector, does not hit for gamma rays, but other charged particles hit CHD. And then we have a fine tracking detector and a calorimeter, and we can distinguish electromagnetic showers from hadronic showers. Electromagnetic showers are well contained and shows regular shower development, but hadron showers have larger spread. So we can distinguish gamma rays from other charged particles. And this is our effective area and sensitivity. This is a plot of the effective area as a function of the direction. And it is mostly actually symmetric, and except some field of view cut imposed by the ISS structure. But still the field of view is about 3 steradians. So about 1/4 of the sky is always monitored. And this is our effective area as a function of energy. We use a high energy, which we call high energy trigger for normal observations. It accepts events above 10 GeV. But for the lower magnetic latitude, And when the GRB fires and caret gamma ray burst monitor, we lower the energy threshold to 1 GeV, which we call a low energy gamma trigger. So normally we are observing in this mode, but 20% of the time we have this 1 GeV lower energy threshold. So we are on the International Space Station, so we can, from our position, we can see the Japanese experimental module, very large module, and there's ISS truss structure is here, and there are solar paddles here, and sometimes it moves around here. They can produce secondary gamma rays from charged cosmic rays, and we have to cut those secondary gamma rays because they are not celestial, but artificial ones. And we have to make masks every day to cut out these structures. And these black dotted events are cut from our data set. And only events from the sky are analyzed, showing red dots here. And this is our gamma ray sky map above 1 GeV, I mean low energy trigger. You can see galactic plane here, and also Vela and Geminga club as point sources. But note that our exposure is not uniform because of the inclination of the ISS orbit of inclination 51 degrees. So we have a large dip in exposure in north and south equatorial regions. So now I talk on the search for gamma ray emission associated with gamma ray gravitational wave events. We are caret is on ISS, and data is not delivered in real time, but delivered every hour. So when the alert from LVC LIGO-Virgo collaboration comes, we start to looking for gamma ray candidates within 60 seconds from the trigger time, and then exposures are calculated, effective area is calculated, and flux or flux limit is calculated, and we have to check overlap with a localization map. And then we issue GCN circulars concerning on our observation. Note that we are about 85% on for the total time. So it is a good monitor for the gamma ray sky, even if it is smaller than the Fermi-Lat. 3 years ago, we wrote papers for energy flux limit for GW events in 2015 to 2017. And colored regions are our field of view on the sky, and green contours are the LVC localization map. So sometimes it overlaps with a field of view, but some are not. And for the neutron-star merger, unluckily, our field of view was out of the LVC localization map. But anyway, we couldn't detect any gamma ray candidates from these events. And then we are continuing our monitor of the gamma ray sky for the gravitational wave triggers. And this is an example of 2019 April 8 events. This just the localization map is almost included in our field of view in this case, but still we do not get any gamma ray candidates here, so we just gave upper limits. And then we are continuing observation of the LIGO-Virgo triggers since then, but still have no events here. So we give gamma ray flux upper limits, and for and here the coverage means and how many % of the sky was of the localization map was covered by our field of view, and then caret light ascension and declination and comment type. So since then we issue GCN circulars almost every time, but still no events are detected. In summary, caret was active for 55 events from the O3 triggers. And in field of view, and we are observing in the high energy normal mode, there are 20 GW events. And in our low energy gamma mode, 6 events were in our field of view, but 29 were out of our field of view. So this is a monthly variation of the caret LIGO O3 alerts showing blue histograms, okay. And orange is our GCN circulars. So we gave 70% of events were reported as GCN circulars. So now the summary. Caret is on board the ISS from 2015 October, and it is monitoring gamma ray sky continuously. And 2 instruments are online, calorimeter and CGBM. And searches for EM counterparts were always executed, but we got only upper limits. But most importantly, we are approved to run the caret experiment until end of 2024, and we are the watcher of the gamma ray sky for the gamma ray gravitational wave counterparts. Thank you for your attention.
Thank you very much. Any questions? So you mentioned that the LAT is more sensitive. How much is the difference between LAT and caret?
In effective area, Fermi LAT is about 10 times larger. But anyway, we are observing the different part of the sky. So in that sense, it is complementary.
Yes. So if we don't have any other questions.
I have a quick question if there's time. Hi, thanks for this great talk. I was wondering, with respect to the gamma ray burst monitor on caret, to what extent can localizations be performed? Because I see these triggers are produced, but without localization.
CGBM does not localize events, but we need other experiments to localize gamma ray location. It's just an omnidirectional detector. It is 2 pi stereo is monitored, but that means localization is not possible by CGBM only.
Okay, so let's thank Masaki Mori again, and our next speaker is Brendan O'Connor.
Hi, everyone. Thanks to Paz for the introduction and to all the other great speakers, especially those talks which introduced Kilonova and Kilonova Afterglows, which will be covered in my talk as well. In this case, I'll be discussing constraints on Kilonova emission in short GRBs at cosmological distances, as opposed to 1708, 17A, which was much closer and has been the brunt of these talks covered here. So a lot of people have already introduced what is a kilonova. So I'll just begin by saying, briefly that they occur after compact binary mergers, like that of 2 neutron stars or a neutron star and a black hole, which we also know to be progenitors of short gamma ray bursts, especially due to the connection that was formed between 1708, 17A and its kilonova AT 2017 GFO. So this is sort of the reason why I'm interested in kilonova emission from short GRBs, because we know that they have these compact binary progenitors, and we expect kilonova emission could be detectable for some of these. So in this work, I'm actually focused on cosmological events, as I said, because kilonova at much closer distances are very, very rare. As you know, a lot of these other talks have said, there's only one case so far, and it's extremely well studied, you know, observed by many, many instruments. And, you know, it's much more difficult to detect these kilonova and or afterglows for cosmological events due to their distances and the fact that they're not, you know, around for as long amount of time. You know, they're not detectable for 3 years like 1708 17As. So in this work, we use the Hubble Space Telescope because it's really the only instrument that can detect kilonova at cosmological distances. And the first GRB for which we provided constraints was GRB 1606-24A at a redshift of 0.483. In the upper right, we see the XRT enhanced position in magenta overlapping a bright galaxy. For this event, we actually did not detect any optical or infrared emission, despite deep searches with Gemini and HST, and actually placed some of the deepest limits on optical and infrared emission for short GRBs in general. So the second event was GRB 2005-22A, which is a completely different event in the sense that we did detect a very bright optical and infrared transient located very close to the center of the galaxy, which is shown in the bottom right. The GRB occurred about 1.1 kiloparsecs from the center, marked by those magenta crosshairs, and the galaxy has a redshift of 0.554. So for the first event, which was 1606-24A, as I said, we didn't detect any optical and infrared emission, so we don't detect a kilonova, but we can actually place very deep constraints on an underlying kilonova because of these upper limits from Hubble and Gemini. So on the left, we show light curves in the HST F160W filter, so like an H band in the infrared. Our upper limits are these downward triangles. And the light curves which we would have detected with these observations are those shown in orange, whereas light curves which we cannot constrain because they just would have been too faint are shown in gray. We see that these kilonova models span a broad range of you know, light emission over time. So it's very difficult to say exactly how many kilonova we would expect to detect based on these observations. But if we consider these models here, we can set constraints on the actual ejecta properties in terms of wind mass and dynamical ejecta mass. Shown on the right, we see this plot of wind mass versus dynamical ejecta mass, and the purple and blue squares are those for which we would have detected kilonova. At least 80% of kilonova we would have detected at 0.1 solar masses for the wind ejecta, and 50% at 0.03 m-sun. So we can actually rule out kilonova with very large wind masses for this event. Whereas these yellow squares, we just wouldn't have been sensitive to. So next I'll discuss 2005-22A. So as I said, very bright optical and infrared transient at a very small distance from the center of its galaxy. Shown here is image subtraction in the Gemini R band and HST F125W band. And we see this transient discovered through image subtraction. This transient is very red in color. The R-H magnitude is about 1.3 magnitudes, which is tantalizing evidence for a kilonova because we know that we expect kilonova at later times to turn redder, as was discussed in Brian's talk. So, however, we only have this one detection and this one color of the kilonova. So because of this, it's very complicated to unambiguously identify this as a kilonova and disentangle from the afterglow, which was also very bright as observed in X-rays. So one of the things we started to do with modeling this event was using a standard forward shock, but including extinction in the host galaxy, as we thought this could help explain the red color without invoking a kilonova interpretation here. So we do find that this model can explain the optical, infrared, and X-ray emission if the dust along the sight line is about 0.1 to 0.2 magnitudes, so not too extreme, but this actually does allow us to explain this R-H color observed between HST and Gemini, and still explain the Swift and Chandra observations and the bright X-ray afterglow. However, another interpretation which we found was equally likely in our modeling was including a kilonova instead of this dust in the host galaxy. So one of the things we did was include an additional blackbody component in our modeling, and we derived confidence intervals based on our MCMC fits for this emission in the different filters for which we observed this transient. Shown here is our confidence region for the HST F160W filter. This box is the 68% confidence, and this whisker line here is our 90% confidence. And we compare this to kilonova models from the Los Alamos National Laboratory Group, and we actually find these 5 axisymmetric models which actually can explain the emission in the 3 bands for which we detected this transient. These light curves are those with very large wind ejecta masses, between 0.03 and 0.1 solar masses. And one of the things I'd like to highlight is that the only way this standard radioactive kilonova can actually explain this emission is if we use these axisymmetric models. And by that, I mean, we have a toroidal disk of dynamical ejecta and a spherical wind ejecta. And the reason this is important is because the emission from the spherical wind ejecta, the optical photons that actually go down towards the dynamical ejecta, will then be reprocessed and emitted preferentially in an on-axis direction in the infrared, increasing this infrared emission without the need to invoke other models for brightening the kilonova. Whereas if we just look at a spherical morphology for wind ejecta, we would not be able to explain this kilonova confidence interval here. And one of the things I'd like to highlight is that the interpretation between this being a kilonova and or dust in the host galaxy is ambiguous because we do not have multiple epochs of detection. We don't have a color evolution for this event. It's obviously not as well observed as 1708, 17A. And because of that, it's very hard to disentangle afterglow and kilonova. And the interpretation is unclear. Both models are equally likely. So I'd like to talk about my work constraining kilonova afterglows and how those relate to cosmological short GBs. Kilonova afterglow has already been discussed by multiple people, so I'll sort of just move past this slide. So one thing we did was observe a sample of about 20 cosmological short GBs with the VLA at varying times after the event occurred. And the reason for this is that we can expect kilonova afterglows to peak and become detectable on timescales of a year to tens of years after the event. So although there might be some evidence for this happening now in 1708, 17A, that doesn't mean that all short GBs would have their kilonova afterglows peaking at about 3 years after the event. It could be 10 years, it could be 20 years. So we need to observe these, a broad sample of GRBs at many different times. So as we see here, this is luminosity in the C-band radio and the time in the rest frame since the event. So some of these actually are about 10 years after, whereas some of them are much more recent GRBs. And these light curves are kilonova afterglows. The red one is for an ejecta mass that is smaller with very high velocity, so it peaks earlier, whereas the green one is that with a larger ejecta mass and a lower velocity, so it's peaking later and at a lower flux. And what we found is that we can constrain the kinetic energy of the ejecta for given assumed masses of the kilonova ejecta. And for kinetic energies greater than 5 times 10 to the 52, we can actually rule those out for wind masses less than 10 to the -2. And in this case, we can actually constrain a powerful magnetar merger remnant for this large sample of short GRBs. which is important to help us move towards an understanding of how likely it is that powerful magnetars or the like form as a result of these compact binary mergers. So one thing we also did was observe GRB 2005-22A at about 6 months post-burst in the rest frame with the VLA, and we can actually begin to derive these constraints even though we observed it at only early times. And future later observations of this event will allow us to continue to rule out a powerful magnetar as the progenitor. So one thing to show here for different densities of the ISM is how the ejecta mass can be constrained over time. So right now, this orange line is when we observed it. And for a density about 10 to the -2, we're ruling out ejecta masses less than 0.03 solar masses. But if we observe this at about 2 or 3 years post-burst in the rest frame, we'll constrain essentially ejecta masses less than 0.1, which is really constraining most of the allowed parameter space for kilonova ejecta, and begins to be very interesting and rule out this magnetar remnant for this event completely. So here are my summary slides, and I would take any questions at this time. If you're interested in learning more about this work, the links to the papers are in the bottom left-hand corner.
Thank you very much, Brendan. Any questions? Yes, I see a hand raised, David.
Yeah, I have a question out of curiosity. When there is not a galaxy associated spatially with the event, how do you calculate redshift?
In that case, we wouldn't really know the redshift. For short GRBs, it's there's only a handful. I think there's maybe 3 of them that actually have redshifts based on optical spectroscopy of their afterglows, but the majority are actually get their redshifts from a galaxy association. So in that case, you would not know the redshift to the event.
Yeah, thank you very much.
Yep.
Any final short question?
I can ask a question.
Yeah.
So especially I've seen for cosmological GRBs, thanks for the nice talk, by the way. But for cosmological GRBs, I mean, there are going to be several explanations, right? Like, for example, Fong et al. Presented 2 possible explanations. So is there a point where you can start really saying that the data are strongly favoring one against some other multiple sets of explanations, and how can you really be sure about the Kilonova sort of interpretation at that stage?
Yeah, you mean specifically, I can specifically talk about 25-22A. You mean like in this case of like, how do you know what the interpretation should be?
Yeah. I mean,
yeah. So in this case, what we actually did was we did MCMC modeling between both of these scenarios, and we can compare the statistical significance of the improvement of, say, the model with the kilonova over the model with just the dust emission. And in that case, the improvement was less than 1 sigma. And we can't say that one of them fits the data better. In this case, we just didn't have enough data to actually prove one interpretation over the other. And I think in that case, I don't think there's anything more you can do. If the data can't tell you that one of these is better than the other, through statistics and the only techniques we can really apply, then I think it's still an open question and ambiguous. For 1708-17A, I think we can actually get more data. And in that case, we can actually continue to understand the significance of this possible kilonova afterglow rise. But for something like this, the transient faded within like 3 days after the merger, and it's lost to us, this actually what happened.
Okay, perhaps this discussion can continue in the chat because we are running late. So thanks again, Brendan. And our next speaker is Dr. Perez Garcia.
Hello. Can you see my screen?
Yeah, we can see.
Okay, so thank you very much. I'm going to talk on neutron star properties and the electromagnetic follow-up of Kilonova. So first I'll present the outline of my talk. I'm going to discuss briefly the link between binary neutron stars and Kilonova, especially that link to properties and model fitting of the sources. Essentially, I'm going to discuss what are the neutron star physics inputs that can be valuable to understand these sources. And then a little bit of follow-up and observation that can be key for understanding these sources. So we have all heard in this session nice introductions about this very important event, the binary neutron star merger that produced gravitational wave 170817. So this essentially produced a broad emission in the electromagnetic channels, and it was possible to detect this on different bands. And we now think that this event was caused by the merger of two neutron stars after a brief previous stage of hypermassive neutron star, or in any case, some unstable state of neutron stars. So there is a very recent Kilonova, neutron star black hole merger that in principle could have produced a kilonova. So far, there is no detection reported. So I'm just putting here for the sake of completion that there are other events that we have to keep an eye on, and probably at some point we will be able to detect those too. So first, a little bit of introduction about what are the sources of these mergers. So neutron stars essentially have a basic nature based on a very large central part, the core of this neutron star, that can attain central densities of about 3, 4, or beyond nuclear saturation densities. So that's in grams per cubic centimeter beyond 10 to the 14. And has some other outer layers named globally as the crust. And in this crust is where matter is less bound and is more inhomogeneous with densities that go all the way theoretically to almost zero density. So to describe this structure, there is a lot of equations of state in the market. I'm just going to focus here on this talk on two cases that we have analyzed a little bit more in detail. So these are the DD2 and the SFHO equations of state. Both are in the market. You can see that in the mass radius diagram that I'm showing here, that both equations of state fulfill some partial constraint that are presently available for these equations of state. So you can see here, this green bar here represents constraints from the gravitational wave event. And the other constraint that you see here come from essentially from determinations and analysis of pulsar measurements from NICER and some other missions. So you can see that some of them fulfill some requirements and some others not. This is the usual picture though. So just a little bit for completion, let me explain that in a neutron star is not always well described by a very high density object, in the sense that when you follow the radial trace from the center of the star towards the crust, you can see that in the outer layers there are some, as I said, inhomogeneous structures, and these structures can actually play a role in the ejecta masses that are shown to be present in giving rise to the kilonova signal. So in principle, these low density layers that can essentially go from 10 to the 11, 10 to the 10 grams per cubic centimeter are the usual density that you can obtain from numerical relativity simulations after the merger in the outer layers. So just to introduce a little bit what is this emission. So it's in principle obtained from a thermalized component of matter. So there are a number of energy sources. Typically, you have photons, you have electrons, you have some very light nuclei, alpha particles, and also some reactions from fission that can give rise to an enhancement of the radiation being processed in the outer layers after the merger. So this is a time-dependent signal. And in principle, there is a way to understand this signal by just trying to standardize the functional form. And there is a very important part of this functional form by the peak magnitudes. So that's, for example, the luminosity peak, the time when it peaks, and the temperature it peaks. And it can be expressed on a parameterized way by expressions. This is just one example. There are many in the market. This is from Dietrich and collaborators, where essentially the ejected mass, the velocity of the ejecta, and the opacity play a very important role. So there is a very important challenge of understanding these parameters in connection to the source properties. So as I said, so far it is a problem that is essentially very complex in the sense that you have to introduce gravitational interaction, electromagnetic interaction, weak interaction physics, and also hadronic physics, all in the same simulation. So the output is essentially, on the electromagnetic point of view, the signal on different bands. But you can try to standardize or to obtain some trends out of these simulations. And here I'm showing just parameterization. There are many authors. I just put here one example where, for example, one tries to feed the ejecta mass and the ejecta velocity as functions that, depending on the ratio of masses of the two neutron stars, the compacity, which is essentially a measure of mass over the radius of the neutron star. For these neutron stars, essentially the compactness is order of magnitude 0.1, which means that gravity is very strong. So you have objects with a typical size of about 10-12 kilometers. There is also a very interesting thing for understanding neutron star physics, which is the difference that is essentially shown in the simulations between the gravitational mass and the baryonic mass. Here I'm just showing that the baryonic mass is this star, and there is a symmetry between the both components. So component 1 and component 2, essentially there is a symmetry in the fittings. As I said, one can try to obtain some trends from the simulations. And the interesting thing here is to see at what extent one can link this to some other neutron star physics that we already understand better, in the sense that they involve nuclear physics and weak interaction physics. So here, as an example, I'm just showing what is the expression for the gravitational mass for a neutron star. So it's just integrating the energy density, which involves not only matter, but also the fields. A baryonic mass, which involves the baryonic density for the object. One has to take care of the fact that you have general relativity effects. So you essentially have that your baryonic and your gravitational mass are different numbers. And when you subtract them, you obtain a measure of what is the binding energy, how much bound is the object with respect to the gravitational mass. So there is a parameterization that can link this baryonic mass to the gravitational mass by obtaining the radius of the neutron star. So I'm just putting here this parametrization that involves as I said, the radius of a 1.4 solar mass object. And you can obtain here that for these two equations of a state we chose, ED2 and SFHO, you can indeed obtain very well enough parametrizations and precision for the radii of these two neutron stars. So all these aspects have to be considered when analyzing the data out of the simulations. So there is another interesting point that at this point I just can discuss qualitatively because we are working on our results, but it is very interesting to show that some preliminary estimates link the ejecta mass in the binary neutron star merger to values of matter in the layers or in the stereo layers of neutron stars. With this, I mean that the mass in the crust of the neutron star, which is expression that depends on the radius of the star, on the compacity of the star, and on the transition pressure, which is the pressure between the core and the crust, the two main layers in the neutron stars. That's when it points to low density and you go towards high density. So this crust mass at some point should be related to the ejecta mass, because at this point what our numerical relativity simulations show is that the very inner part of the neutron star does not get ejected in the merger. So it is only the binding energies that are put into play are those capable of stripping the outer layers of the neutron stars. So for these two equations of state, it happens that the crust masses are about 0.04 solar masses and 0.02. So that's about 4% of solar masses, which is not far from the full ejecta masses when measuring, or at least is an upper bound for the disk and dynamical ejecta masses. So another interesting point is that the number of baryons should be conserved, since all these reactions post-processing the matter ejection do not involve change in the baryon number. A different aspect is computing the opacities. So the opacities typically are taken for as another source that can be related to the neutron-rich matter. So I'm just showing here some plots from work of Tanaka and collaborators and some other people, where you can see that depending on the wavelength, the radiation that is considered, there are multi-component system that gives rise to an opacity that is a changing function. So it changes with the lepton fraction, and it changes, of course, with the wavelength. Let me remind you that the lepton fraction changes because we have these weak interaction reactions going all over, and all these neutrino winds. So you have, in addition to that, the beta decay reactions and some other reactions involving neutrinos. So you have these changing fractions. So in our case, we chose to study, considering these two equations of state, some additional cases already studied by Radice and collaborators and some other people as well. And we consider a two-zone model where essentially there is an isotropic emission where you have a blue emission and a red emission with this lanthanide-rich region is parameterized by an angle phi. So you can see
we
here
should
that
summarize, we are running very late. Sorry to interfere.
Yes, yes. Okay, so just give you an example of what we obtain. For the luminosities, we essentially determine by using POSIX simulation for luminosities and spectra that the orientation is very important for extracting physical observables. You can see here as an example that from phase on to edge on, you can have that your luminosity, the peak value of the luminosity, and also the decay of the luminosity curve change. So this is important when extracting the values for the ejecta and velocity masses, and also an average value of the opacity. So this is especially true for the two first days, for example, in this particular example, but is less important for times up to 2 weeks. You can see here as another example, the fluxes.
You may have to stop here. I'm sorry. We simply don't have much time. Do you want to maybe jump to the conclusions?
Okay. Yeah, I'll explain this if you don't mind, and I'll stop here. Is it okay?
Yeah, it's okay.
Yes. Okay, so essentially this is the interesting, most interesting part, I think, from previous results that we have been able to obtain. So you can see here that for the very early spectra, so 0.5 days and 1 day, that for two different equations of state, that's DD2 and SFHO, yellow and blue curves, that one could, in principle, be able to obtain if one is able to obtain good pointing at the source and so on. But you can see that there is a big difference here. So it doesn't mind the orientation much in this respect, but for these two equations of state, the error bars when determining this particular merger regarding the equation of state, there is a difference that could be seen. So this is for 0.5 and for 1 day. So just to wrap up. So this difference essentially comes from the fact that the ejecta masses coming from the gravitational mass of both neutron stars in the merger get more asymmetric as the two objects are more asymmetric. So this is the main point, and we want to explore the dependence on this with the equation of state.
Thank you very much, and sorry that we are so short on time, and we will therefore not have time for any questions, but I encourage people to ask questions in the chat, and perhaps this discussion can also continue beyond the session. So let's quickly move to the next speaker, which is Alessandro Drago.
Yes, thanks a lot for the possibility of presenting our recent work here. And so we will also discuss the relation between Kilonova signal and the equation of state. These are the main points. The main points are that there are parameterization that have already been mentioned by the previous speaker, which is essentially allowing us to estimate the amount of mass which is not immediately swallowed by the black hole, so finishes in the disk or is dynamically ejected. And this parameterization estimates this mass in terms of the tidal deformability and the compactness of the neutron star. So since NICER has now provided some interesting limits on the radii, we can use this information. And essentially what I will discuss in a few minutes is there any possibility of distinguishing between what you get if there is only one family of neutron stars, meaning only neutron stars in a traditional sense satisfying the limit of NICER, and distinguish this possibility from the possibility in which there are two families of compass stars, namely one is made of neutron, protons, hadrons, hyperons, and the other is made of the confined quarks. If the other is strange quark stars, the answer is a yes, in the sense that, as I'm going to show very rapidly, in the second case, we expect to have an extremely weak Kilonova signal because there are two results. The first result is that quark star, strange quark star black hole do not produce any kilonova signal. This is a simulation made 20 years ago by Krusniak and Lee. And the second point is that neutron star having small radii, which is the typical situation in this two-family scenario, then the ejected mass is very small, exactly because the radii are very small. So let me rapidly go through these ideas. First point is there is a very direct relation between the radius of a neutron star having a mass, let's say 1.5 solar masses, and the tidal deformability, almost a linear relation, large range of values of mass, large range of values of radii and tidal deformability. Second point is that NICER has now provided us with very interesting limits concerning the radii. These are the limits obtained from the new object, this object here, rather large radii for an object of 2-point-something solar masses, combined with previous analysis of a different object by NICER, combined together by Miller in these limits on the radii. So this is what we are going to use. We are using essentially the limits on the radii obtained by the analysis of Miller, and we discuss three representative equations of state, which, as you can see, are essentially spanning completely the possibilities which are still allowed by the analysis of Miller, going from the softest equation of state, the black one, to the stiffest equation of state. So this translates into a clear difference in the tidal deformability. As I was mentioning, radii and tidal deformability are strictly related. So equations of state which have very large radii correspond to equation of state having large values of the tidal deformability. So these three lines are essentially what you get concerning the tidal deformability if there is only one family of neutron stars, the normal scenario. The other lines, in particular these two lines, the green and the red, they correspond to what you would get if instead there are two families of neutron stars, in particular hadronic stars having small radii. I don't have time to discuss in reality what is this two families scenario. We have published many papers in the last 7-8 years. Essentially, as I was mentioning, it corresponds to the idea that you have neutron stars that actually are made of neutrons, resonances, hyperons, and they can be very compact, but they don't reach to solar masses. And at the same time, you can have strange quark stars that can reach large masses, but they have large radii. There are several arguments in favor, so to say, of this scenario. In particular, for instance, there is a bimodality in the mass distribution that is almost exactly reflected from what you would get in this scenario, but I don't really have time. Let me just mention one thing. In this paper that we are now submitting for publication, we compare the NICER results with what we get with our strange quark star family. This is based on a Bayesian analysis, not obtained, not using the last result of NICER. So in a sense, this is a prediction of a strange quark star model. And as you can see, it fits perfectly with the latest NICER results. So in conclusion, what do we claim concerning the Kilonova signal in this scenario? We are using, as I was mentioning, parametrization made by several groups, in which essentially you can compute those two masses if you know the tidal deformability of your star and the compactness. This is what you get from the equation of state. And these are the results. The results are quite striking, I would say. On the left column, these two figures here, are the results in the standard scenario. This is what you get if you use an equation of state that passes literally through the center of the values indicated by the analysis of Miller. This example here MPA1 that we are using is what you get. And you see, if you compare with what you get in the two family scenario, you see that, for instance, the mass of the disk is different from 0 in a much smaller region of masses of a black hole and of spin of a black hole. And similarly for the mass dynamically ejected. Why is that? Because in the two family scenario, we are assuming that it exists a first family of objects which have very small radii, and therefore small tidal deformability, and therefore very difficult to eject mass in a neutron star black hole merge. Even more clear in this second slide, here we have fixed the mass of a black hole, fixed the spin of a black hole, and again we are computing the mass dynamically ejected, the mass of the disk, as a function of a massive neutron star. Just an example, look at 1.3 solar masses, very typical mass. As you can see in the normal scenario, these three lines correspond to the equation of state, which are completely spanning the limits of Miller. So essentially, this is all what you can get in the standard scenario. And you see that for a 1.3 solar mass object, you definitely have a finite amount of mass dynamically ejected, and you get essentially 0 in this alternative scenario, and similarly in the mass of a disk. So these are my conclusions. The conclusions are that if you study the Kilonova signal in the neutron star black hole merger, there is a very clear difference between having one family or two families. Message is, if you have one family and you use nicer results, you expect to have a lot of mass ejected. If you use nicer results within two families, you expect to have essentially no mass ejected, therefore no Kilonova signal. So there are other things, but I don't have time to discuss other possible signature of the scenario. But this is what we can realistically expect to see in the next years. Thanks a lot.
Thank you very much. One quick question, maybe. Okay, if not, then let's move to the next speaker, which is Eron Tovovo.
Hi, can you hear me? Yes?
Yes.
Ah, great. And you can see the screen? Okay,
Yes.
Great. My name is Aaron Tovovo. I'm a PhD student at the University of Toronto. I'm going to talk today about trying to localize gravitational wave sources to ICRANet precision from the prompt emission alone to enable access to early time physics. And this work was done with a lot of people, but most notably Jimmy Delany, who just graduated and got his PhD at Penn State. So I'm going to show this plot again, even though Brian showed it earlier. It's a great plot. Just to highlight, right, that there's all this early time phenomenology, things like the extended emission or plateau from the X-rays, early neutron precursors, other things like if you want access to the nature of the post-merger remnant in early times, and even for GW 170817, we saw that really early time UV observations are crucial to break the model degeneracies to explain the emission that we see. And so this is really just to motivate that we want to get on target to these gravitational wave detected mergers at really early times to access, tons of really cool physics. But this is hard. What you're looking at here is a image from the gravitational wave treasure map, which I built with Sam White at the University of Arizona. And you're looking at an image of the coverage for gravitational wave 190814, which is a high mass ratio merger, possibly a neutron star black hole, with one of the component masses below 3 solar masses. And this is the most well covered and searched gravitational wave source to date. The final gravitational wave localization was less than 20 square degrees. Over 20 instruments from radio to gamma have reported their coverage to the treasure map with over almost 4,000 individual search exposures. And so the total coverage here looks really good. If there was something there, we probably would have found it. There probably wasn't something there, right? Because the mass ratio was so high. But when you look at the actual time profile of the coverage, even though the total coverage of this event was exceptional, what you see is that within the first few hours, what you're looking at is the fraction of the total gravitational wave localization posterior covered in all wavebands as a function of time. you're seeing that within the first few hours, and even within the first day, it really wasn't adequately covered to find early time physics, even if there was something there to find. And obviously, there are people working on next generation facilities, including myself, that will do these searches even faster and cover the gravitational wave regions faster to find counterparts like Kilonova and Afterglows. But even in these cases, there will be a delay from the time where the source is so-called discovered by the Wide Field Survey Facility, and when sensitive follow-up with our most sensitive instruments like HST, Chandra, and VLA can begin, because of things like needing classification with spectra, disambiguating from background supernova and variable sources and all these things. So what, in the best case, right, we would be able to localize a gravitational wave source to within the field of view of our most sensitive facilities like Hubble and Chandra from the prompt emission alone at very early times. For some gravitational wave sources, there will be a gamma ray burst associated with it. We saw this for GRB 170817. GRB 170817 had an inclination angle of, we've heard somewhere between 20 to 30 degrees, and 30 degrees is at the peak of the gravitational wave instrument inclination angle selection function. So a non-trivial fraction of gravitational wave detected by neutron star mergers will have gamma ray emission associated with them. If you're familiar with things like Fermi GBM or Kelet, which we heard about before, these range from localizations of GRBs from hundreds to thousands of square degrees to no localization capability. But coded aperture instruments, which effectively computationally image the sky via shadows, are capable of localizing gamma ray bursts to arc-minute precision from the prompt emission alone. The Swift Burst Alert Telescope is the most sensitive and largest coded aperture instrument ever launched. It sees about 7,000 square degrees of the sky at any time and produces arc-minute localizations at 10 seconds post-burst for about 100 gamma ray bursts per year. And I can explain more about how this works if people have questions. But we can't rely on the onboard algorithms running onboard Swift or actually any GRB facility to find these GRBs, because they're really faint. What we saw with GRB 170817 was that it was underluminous compared to the cosmological population by a factor of 1 to 10,000. GRB 170817 would not be detectable by Fermi or Integral, even in targeted ground-based analyses beyond 60 to 70 megaparsecs. So we really need sensitive analyses of these instruments to find these GRBs, and in the best case, we need a new, high effective area instrument like Compton, but we're not going to get that. Intrinsically, BAT is the most sensitive GRB detector. It would be capable of detecting a GRB 170817-like event out to 100 megaparsecs, or even a little bit beyond that, which is almost 2 times as far as any other instrument. And crucially, it's the only instrument that can provide these arc-minute localizations that you need for very early time follow-up. But in order to do this, you need the time-tagged event data, which is each count detected by the detector tagged with photon, energy, and detector location. And the problem is that typically for Swift, these data aren't on the ground. Swift does not have time-tagged continuous event data. This is because the effective area of that is massive, which produces a high data volume, and the bandwidth downlink is limited. However, this data is saved in an onboard ring buffer, which lasts about 20 minutes, as you can see on the right. And so if we could get a command up to Swift in this time scale, we could save this time tag event data, bring it down to the ground for really sensitive analyses. But before a year ago, the fast response commanding that Swift achieved, which was already faster than anybody else, was order 2 to 4 hours, which is not suitable. So we spent a few years working on this, and we finally succeeded. The system is called Guano, the Gamma Ray Urgent Archiver for Novel Opportunities, and it now consistently achieves order 15 to 20 minute command arrival on board from T0 triggering time, and it does this about 5 times a day now with an event data recovery success rate of over 90%, and has now done this about 1,500 times in the last year and a half. And now we have the event data on the ground. We can do these really sensitive analyses. But what we discovered is that typical coded aperture mask imaging, which works by taking the shadow produced on the detector and cross-correlating it via a fast Fourier transform with the coded mask image, is intrinsically limited in its sensitivity. And this, you can see on the right that there's this large image noise population at low signal noise ratio that totally dominates the real signal. The real signal is things above SNR of about 7. And you can see if you do a log linear extrapolation, there are signals hiding in the image noise in BAT, but they're completely unrecoverable because of this huge noise population from the imaging procedure. And in addition, imaging totally rejects uncoded counts. So this is counts that land on the detector without going through the shadow mask. And this gives up information. It also neglects energy information, which gives up possible localization. And it also has a lower effective area at higher energies, i.e. short hard GRBs, because the mask becomes transparent at these energies, even the lead in the mask. So we've been developing a new search technique. It's called nitrates, the non-imaging transient reconstruction and temporal search. basically what we do is we forward model GRBs through the entire Swift burst alert telescope response function and produce model shadowgrams. The data that you're looking at on the bottom of the screen images are not data. These are simulated models of what a GRB at certain fluence at a certain angle with respect to detector would look like. And then we perform a likelihood test where we compare these models to the GRBs. And what you see is that even in the non-coded regions, so the coded region is this highly modulated thing, which, you know, in imaging is what it contains the sky location information, but there's also large parts of the detector array, depending on the position of the GRB, that are uncoded, but still have counts on them. And this has information about the location of the GRB encoded in it. And we figured out a way to use this information, and this paper is coming soon. It's led by Jimmy, and it results in a search that can be 5 times more sensitive than imaging in the best case, and still substantially better. So this is running. What you see here is a comparison on a typical GRB. On the left, you see conventional coded aperture mask imaging. You see this large noise population in orange, and the position of the true GRB in blue, versus our nitrate search on the right, where you see the noise population is dramatically decreased and the significance of the true GRB position increased. The cost here is a factor of about 1 million in computation time. So the conventional code aperture mask imaging on the left with fast Fourier transform can run about 10 seconds or less, and the one on the right takes about 500 CPU hours. But it can do a lot better. And if you have a big enough cluster, you can make that run fast. So we did this during 03. What was that?
1 minute.
Okay, we did this during 03, and we brought down, for even subthreshold gravitational wave triggers via MOU, and we brought down 100 TT data via Guano for hundreds of gravitational wave triggers. There are no strong candidates, but we have improved our search, and we'll report our offline analysis in papers that you should look out for coming soon. We also started dumping guano data for GRBs that were triggered by other instruments but missed by BAT on board, and this has been exceptionally productive. In the past 1.5 years, we've produced ArcMinute localizations for GRBs at a rate now of about 1 per month, which is substantially higher than what people assumed BAT was missing. This was over 15% of all ArcMinute localized GRBs last year were found by guano and nitrates. It also has a higher short GRB recovery fraction than BAT does on board, about 1/3 versus 10% for the onboard algorithms. And this has to do with, the better sensitivity to higher energy GRBs. And we are producing localizations and distributing the community in order hours to average localization distribution now is about 8 to 10 hours. 13 of our 18 ArcMinute localized GRBs were suitable for prompt follow-up. And of those 13, 6 have had X-ray afterglows discovered. And for the other ones, they have had their localizations, some of them have had their localizations confirmed by things like IPN. So of course, however, yeah, I'm finishing up right now.
Maybe if you have a summary slide.
Yeah, I'm finishing right now. So of course, the BAT only covers 1/6 of the sky. So even with its increased sensitivity of these searches, it's still the joint GRB gravitational wave detection yield still is not higher than things like all sky instruments, which have less range. But you can exploit the shape of the gravitational wave detector patterns to bias the scheduling. And you should look out for this paper here I have with the Sorab coming up, where we basically increase the effective field of view of BAT with respect to gravitational waves from 1/6 of the sky to 1/4. I'll finish with this summary slide and stop for any questions if there are any. Thanks for your attention.
Thanks a lot, Aaron. Unfortunately, we don't have time for questions. So again, people should write their questions in the chat, and perhaps this discussion can continue there. Let's move to our final talk of the session. And this is a talk by Fergus Hayes.
Hi, can you hear me okay?
Yeah.
Okay, yeah, I know we don't have much time, so I'll try to go through this as quickly as possible. So I've been working on this with Seong Heng and John Veach at the University of Glasgow, as well as Gavin Lamb from the University of Leicester. So I'm looking into jet structures to explain the dimness of GRB 170817. We know a lot about the jet structures from the previous slides, so I won't go too much into them, but looking particularly into the top hat jet, structured jets, and cocoon models to try and explain the dimness. So we're looking to see whether we can find jet structures that can explain the observed rate of short GRBs, the prompt emission of 170817, as well as the gravitational wave emission, and the gravitational wave emission from 190425. So just a quick look at the data that's used. So on the right side, we consider the short GRB rate to be taken from Swift observations over a 9.8 year period. There was 107 short GRBs detected by Swift. And here you can see the gravitational wave posteriors that we use for the analysis. On the left is 17.17, and on the right is 19.0425. This shows the distance and viewing angle posterior samples that are used. And lastly, on the GRB side, the fluence of GRB 17.17 detected by Fermi was 2.8 times 10 to the minus 7 ergs per square centimeter with about 10% uncertainty, while for 19.0425, since no counterpart was detected, we assume that to be 0 and assume the same uncertainty as 17.17 for it. This data is entered into the likelihood in our Bayesian analysis, which is specified just on this bottom line here. So just jumping straight into results. So the first structure that I consider is the top hat jet. That's parameterized in this bottom left-hand panel here, where we see the shape function over viewing angle for both the energy and the Lorenz factor, where the energy is the red dashed line and the Lorenz factor is the yellow dashed line. And they're both, for a top hat jet, parameterized by a single parameter theta j. And the black line here is the isotropic emission that results from those two distributions. So on the right-hand side is the posteriors for the analysis given different data sets. So there's three different combinations of data. First off is when I feed the analysis just the rate data, which results in this black posterior here. And then given in addition the 17.17 data, we get the blue posterior, and with the reds, that's including 19.0425 as well. So we can see with, when we just look at the rates, there's a relatively low theta j that's estimated by the posterior, but with the increased information, we get a higher opening angle, and the posteriors close around a value of around 5.7 plus or minus 1 degree. So now just looking at the first structured jets, considering a Gaussian jet, which is parameterized just in this bottom left-hand panel, where both the energy and Lorenz factor distribution are parameterized by a single width parameter theta sigma. And we can see similarly in the right-hand side, the posteriors, given more information, close around a relatively tight value of the opening angle, around 2.3 degrees. And we can see on the bottom left-hand panel, the isotropic emission that is produced from this agrees quite well with relatively with the position of GRB 17.17. Secondly, looking at a parallel jet structure, this is parameterized by being uniform over angle, like the top hat jet, until some critical angle, after which it decays both in energy and Lorenz factor with gradients A for the Lorenz factor and S for the energy. The posteriors on the right-hand side here, we can see that there's not much information gained given 17.0817 and 19.0425, and most of the constraints are made just by the rates. But we do get relatively tight constraints given this. So the core angle is actually constrained to be a narrow 1.2 degrees, plus or minus 1. And the gradients for the energy is relatively steep to be 3.4, while the Lorenz factor gradient is gentler in comparison with 1.4 in gradient. And we can see also that the isotropic emission in the black line agrees again very well with DRB 17.817a. Now, the third, the last structure I'm considering is double Gaussian jet. So this is to resemble something that's a bit more like a cocoon structure. And this is parameterized, as we can see at the bottom, with two Gaussians. One, the inner Gaussian to describe the core of your GRB, you can see is described by width theta in. And the outer part, which is the cocoon shell, is described by width theta out. And these parameters A and C are to denote the fraction of the energy and the Lorenz factor of the cocoon in comparison to the core for this structure. Now, similar to the parallel jet, the posteriors that come out of this analysis do not gain much information when including 170817 and 190425 and are mainly constrained by the rates. But yet again, we do get relatively tight constraints where theta in is a very narrow 2 degrees and theta out is also surprisingly narrow at 4.7 degrees. This is compensated for by large fractions for the core energy, the cocoon energy and the Lorenz factor, where the energy is said to be about a fifth of the core and the Lorenz factor is half of the core. However, there are large error bars on this, so should be taken with a grain of salt. Now, I wasn't talking there about the BNS rate posteriors that come out as well. So I've gathered them all up and just plotted them here. And for each of the individual jet structures and comparing them to the result from GWTC2, which on this plot is shown by this blue line. This is also compared to the prior distribution, which is roughly taken from the BNS rate from GWTC1. Now, all the jet structures produce a BNS rate that roughly agrees with GWTC2's BNS rates, apart from the power law, which has a higher BNS rates in comparison. Now, here I've tabled up the log evidences for the different jet structures given the different data sets. So if we just look at the bottom line, we can see the log evidence given all the data on both events. And the log evidences that come out for the highest for the what jet structures is the analysis supports the Gaussian and parallel jet structures over the top hat and double Gaussian. In fact, the double Gaussian is severely disfavored in comparison. However, the top hat jet structure is lower than the parallel and Gaussian jet structures, but is not should not be discounted.
We should stop in 1 minute because the session will be automatically stopped by
This is my final slide. So looked into in previous work, looked into how to distinguish between these jet structures given future events. So with simulated events of gravitational wave triggered events with short GRBs attached, one population of which has parallel jets and another with Gaussian jets. So in this plot, the blue represents parallel jets and the purple represents the Gaussian jets. And we calculate the log evidence for each of those models with different subsets of events. So the difference between the log evidence of the parallel structure and the log evidence of the Gaussian structure is plotted here on the y-axis. And you can see with increased number of events, we're able to get more and more confident in distinguishing between these two data sets. So yeah, I'll just leave my summary slides there. And that's me done.
Thanks a lot, Fergus. Any final critical question? We have really just a couple of moments before the session is closed. Okay, if not, then I want to thank all the speakers for a very nice session and really many nice talks. A lot to think about. Unfortunately, we didn't have much time to discuss everything, but hopefully this will get some discussions going offline as well. So thanks, everyone.
Thank you very much.
Thank you.
Thank you, guys.
Thank you. Thank you.
See you, Yoni.